Something is wrong in the sky. For centuries, the faint smudge of Andromeda has whispered to us from 2.5 million light-years away, a ghostly lantern just visible to the naked eye on crisp autumn nights. We thought we knew it. A simple spiral galaxy, our neighbor, our eventual dance partner. But every new telescope, every new measurement, has betrayed our assumptions. The more we look, the less we understand. Now, for the first time, astronomers believe they finally know Andromeda's true size, and the answer is unsettling. It is not merely large, it is monstrous. Its arms stretch farther than we imagined, its halo of dark matter swells beyond calculation. Its gravitational influence reaches out like invisible fingers brushing against our own Milky Way. The quiet smudge in the sky is not a distant ornament, it is a giant, pressing against the edges of our cosmic neighborhood, already shaping our fate. What if Andromeda is far bigger than the Milky Way? What if its shadow has always been upon us? And what if its approach is not a gentle meeting, but the prelude to something stranger, something no human mind has yet dared to picture? Part 1. The Colossus Next Door. They told us Andromeda was large, but no one told us it was this large. For decades, astronomers compared our Milky Way to Andromeda as if they were twins, two spiral galaxies of similar size, similar grace, orbiting in the quiet of the local group. That story was comforting, even poetic, a cosmic balance between neighbors. But the new measurements break that illusion. Andromeda is not just another galaxy beside us. It is the most massive, most sprawling, most dominant structure in our cosmic neighborhood. What we once thought of as a smudge of light, something fragile and barely visible to the naked eye, has been revealed as a titan. If you stand beneath a clear night sky, far from city lights, you may glimpse it. A faint oval glow, smaller than the tip of your thumb held at arm's length. The human eye cannot see detail, but within that blur lies a galaxy over 220,000 light-years, across twice the size of the Milky Way's luminous disk, and around it swirls an invisible cocoon, a halo of dark matter and gas stretching nearly 1 million light-years in diameter. 1 million light-years, a size so overwhelming that if our eyes could detect it, Andromeda would dominate the sky. It would not appear as a blur. It would sprawl from one constellation to the next, a continent of starlight draped across the heavens. How could we have missed it? For most of human history, Andromeda was thought to be a nebula inside our own galaxy. It was only in 1924 that Edwin Hubble, using Cepheid variable stars as cosmic yardsticks, proved that Andromeda lay far beyond the Milky Way. That discovery alone doubled the scale of the known universe. Suddenly, galaxies were not clouds within our own system but island universes, countless and far-flung. Yet even then, we underestimated. We saw the brilliant spiral, measured its brighter stars, and assumed the rest. Only in the last 2 decades, with Gaia mapping the motion of individual stars, with Hubble charting the faint flickers at the edge of vision, and with the James Webb Space Telescope piercing the dust of the halo, did we begin to glimpse the full enormity. Andromeda was not equal to us. It was larger, more massive, more complex. Think of the numbers. Over 1 trillion stars blaze within its arms, compared to the Milky Way's estimated 400 billion. Its central black hole is at least 100 million times the mass of the Sun, 10 times heavier than the one anchoring our own galaxy. Its stars whirl around the core at speeds approaching 250 miles per second, nearly 1 million miles per hour. At that velocity, you could circle Earth in less than a minute. And yet, all of this is only the visible part. The real bulk of Andromeda, the thing that makes it the most massive galaxy in the local group, is dark matter, unseen, untouchable, known only by its gravitational pull. It is this invisible halo that pushes Andromeda's true size close to that impossible million light-year figure. And here lies the most unsettling truth. Our own Milky Way has a similar halo, and the two halos already overlap. In other words, the collision of Andromeda and the Milky Way has begun. We often hear that the galaxies will collide in about 4 billion years, their disks merging into one vast elliptical galaxy. But that language is misleading. The visible galaxies will not meet for billions of years, but their invisible halos are already touching. Gravity has linked us. Our fates are intertwined. The cosmic dance is underway, even if our eyes cannot yet see the steps. Andromeda is also a cannibal. Streams of stars curve across its outskirts like rivers of light, the remains of galaxies it has swallowed whole. Over the past billions of years, Andromeda has consumed dozens of smaller companions, tearing them apart and folding their stars into its trillion-star family. The evidence is written in those tidal streams, faint arcs unraveling in its outer halo. Each one tells a story of destruction. And as the largest galaxy in the local group, Andromeda will continue its feast until the Milky Way itself becomes its partner in collision, perhaps even its prey. But even now, despite all our progress, we do not fully understand Andromeda. Why does its central bulge seem so quiet, its stars old and dim, while its spiral arms burn with newborn suns? Why is its dark halo so extended, reaching nearly halfway to our galaxy? Why do its satellites swarm in strange alignments, as if caught in a web of unseen order? Every question we answer creates new mysteries. The more we measure, the less we understand, and yet, there is something poetic in this uncertainty. Humanity has always looked up at Andromeda. Ancient Persians recorded its faint glow. Medieval astronomers drew it in their sky maps. And now, with our satellites and telescopes, we see it as a giant stretching across space, perhaps the largest spiral galaxy we will ever touch. Imagine that. The most massive galaxy in our local universe is also one of the few we can see with the naked eye. It has always been there, whispering its enormity, waiting for us to notice. And tonight, as you close your eyes, imagine Andromeda not as a blur but as what it truly is, a leviathan of stars, a trillion suns rising and setting across a disk 200,000 light-years wide, wrapped in an invisible cloak 1,000,000 light-years across. Imagine that cloak already brushing against our own galaxy, entwining us in a future neither galaxy can escape. This is the story of size, of scale, of revelation, but it is only the beginning. For how do we know? How do we measure something so immense that light itself takes millions of years to cross it? How can fragile creatures on a small planet stretch their rulers across such distances? The answer lies in a sequence of clever tricks, in candles of starlight and shifting parallax, in the work of satellites like Gaia and telescopes like Hubble. And that will be our next step. Before we drift into part 2, let me pause here, softly, with gratitude. If this gentle voyage has given you even a small moment of peace, I am deeply thankful you shared it with me tonight. A quiet like, or a soft tap on subscribe, is more than just a click, it is encouragement, a way of telling me these night journeys are worth continuing. And if you would like, I would love to know where you are listening from, your city, your night sky, your place beneath the stars. Your words, whether brief or long, are like little constellations guiding me forward, and I treasure them deeply. In part 2, we will explore how astronomers dared to measure Andromeda, the flicker of Cepheid stars, the careful mapping of Gaia, the whispers of redshift, and the precision of the James Webb Space Telescope. With these rulers of light and time, humanity finally stretched its reach across the gulf and uncovered the full immensity of our neighbor. Part 2. Rulers of starlight. How do you measure a giant? How do you hold a galaxy in your hand, stretch your ruler across 2 million light-years, and whisper, "This is its size"? The challenge is absurd, almost laughable. And yet, somehow, humanity has done it. We stand on a small world orbiting an ordinary star, and yet from here, using only the fragile language of light, we have stretched our reach into the vastness. And the story of how we measured Andromeda's true size is not just a tale of instruments and data. It is a tale of faith, of imagination, of human persistence. It is the story of how we dared to believe we could weigh the heavens. The earliest attempts were crude. In the 17th century, Galileo looked through his telescope and saw Andromeda as a faint cloud of stars. Astronomers catalogued it as a nebula, unsure if it was inside the Milky Way or beyond. For centuries, its distance was a mystery. Was it a neighbor inside our own galaxy, or a universe unto itself? The answer required a ruler long enough to span unimaginable gulfs. That ruler came in the form of stars that pulse, Cepheid variables. These remarkable stars brighten and dim with exquisite regularity, like cosmic heartbeats. Henrietta Leavitt discovered that the longer their cycle, the more luminous they truly are. If you know how bright something should be, and you compare it to how faint it looks, you can calculate how far away it is. It is like looking at a lighthouse across the sea. If it seems faint but you know its bulb is powerful, It must be very far. In 1924, Edwin Hubble used these Cepheid variables in Andromeda. He measured their pulses, calculated their distances, and in one breathtaking stroke, proved that Andromeda was not a cloud within the Milky Way. It was another galaxy, an island universe. For the first time, humanity understood that the Milky Way was not the cosmos itself, but one among countless galaxies adrift in an ocean of night. That discovery shattered the boundaries of the universe, but it was only the beginning. Cepheids gave us distance, but not the full measure of size. To stretch across Andromeda, astronomers needed more tools. They turned to redshift, the stretching of light as galaxies move away from us. They used parallax, watching stars shift against the background as Earth orbits the Sunday. They found standard candles beyond Cepheids, type Ia supernovae, exploding stars of predictable brightness. Each was a step on what astronomers call the cosmic distance ladder, a sequence of overlapping methods that allow us to measure farther and farther. At each step, the picture of Andromeda grew clearer and larger. But it wasn't just about rulers of light. It was about rulers of motion. In the late 20th century, astronomers mapped the rotation of stars within Andromeda. They expected the outer stars to slow down, the way planets in the solar system slow as you move outward from the Sunday. Instead, the stars on the edge of Andromeda were moving nearly as fast as those near the center. This should have been impossible unless something unseen was adding mass. That something was dark matter, a hidden halo of invisible particles, outweighing all the stars combined, stretching hundreds of thousands of light-years beyond the visible disk. It was dark matter that revealed Andromeda's true immensity. Suddenly, the galaxy was not 220,000 light-years wide, but closer to 1,000,000. What we saw was only the tip of the iceberg. The rest was hidden, like a vast shadow beneath the waves. Gaia, launched in 2013, transformed the picture again. Orbiting Earth, Gaia measures the positions and motions of over 1 billion stars with incredible precision down to the width of a human hair, as seen from 1,000 miles away. With Gaia's data, astronomers trace the subtle motions of stars within Andromeda and its satellites, refining the galaxy's mass and confirming its overlordship of the local group. Gaia showed us that Andromeda's gravitational pull is not confined to its spiral arms. It shapes the motion of entire dwarf galaxies around it. Then came the James Webb Space Telescope, opening its golden eye in 2022. With its infrared vision, Webb looked through Andromeda's dust clouds, revealing hidden clusters and faint stars at the galaxy's edge. These faint stars, nearly invisible to Hubble, became new markers of distance. Webb allowed us to weigh Andromeda's outermost regions, extending our ruler farther than ever before. Each new layer confirmed the same haunting truth. Andromeda is bigger than we thought. Always bigger, always more massive. It is as if the galaxy resists being measured. As if each new instrument we build only shows us the next veil to lift. We say, here is its size, and then discover we have underestimated again. The more precisely we measure, the larger it becomes. And yet, in this strangeness lies beauty. Imagine the patience of light itself. Photons leave a Cepheid star in Andromeda, travel for 2.5 million years across the Gulf, and finally arrive in our telescopes. For all of human history, they were already on their way. Every pulse of light is an ancient messenger. Every flicker is a signal across time. When Hubble saw those Cepheids in 1924, the light had begun its journey long before humans existed as we know them. And when Webb peers at Andromeda's edges, the faintest stars it sees may have been shining before our ancestors walked upright. What if we think of measurement not as rulers and numbers, but as conversations with the past? Each method is a way of listening to ancient voices, of piecing together the story of a galaxy so vast that it takes millions of years to speak to us. Andromeda's size is not a number. It is a memory written in light. And there is a deeper mystery still. The tools we use, parallax, Cepheids, Gaia. Webb assumed that the laws of physics are uniform, that light behaves the same across all space. But what if it does not? What if the cosmos bends rules in ways we do not yet understand? Already, we see tensions between different methods of measuring the universe's expansion. Could the same be true within our local group? Could Andromeda's immensity be telling us not only about itself, but about hidden laws of the universe? Imagine, for a moment, if our rulers are flawed, if Andromeda is even larger than we think. What if the million light-year halo is only the beginning of a still vaster web? What if its true boundary lies beyond our grasp, stretching into regions we cannot yet detect? The possibility hangs over every measurement, the suspicion that the galaxy we think we know is still stranger than we imagine. And this uncertainty is not weakness, it is wonder. The fact that we can stand on a pale dot called Earth, send machines into orbit, and measure the size of a galaxy millions of light years away is already extraordinary. That we can do it imperfectly, knowing our rulers may need to be rebuilt, is part of the poetry of science. So tonight, let the numbers drift like stars across your mind. 220,000 light years, a million light years, 1 trillion stars, a black hole 100 million times the Sunday, and yet none of these captures Andromeda's true scale. It is not just a giant, it is the ruler of our skies, the colossus next door, and this is only the beginning of our journey. For knowing how large Andromeda is forces us to confront another deeper truth. Size is not destiny. What truly matters is motion. Where is this giant going? What path is it on? What will happen when Andromeda, with all its mass and all its stars, collides with our Milky Way? That is the story waiting for us in the next chapter. Part 3. When giants collide, there is a prophecy written in the stars, not in ancient scrolls or forgotten myths, but in the cold numbers of celestial mechanics. Our galaxy, the Milky Way, is on a collision course with Andromeda. Not perhaps, not maybe, but inevitably. The fate of our night sky has already been decided. Astronomers have run the numbers, and they all agree. In about 4 billion years, the sky will begin to change, slowly at first, then more rapidly. Andromeda, that faint oval blur you can see tonight if you step outside, will grow larger and brighter. Over millions of years, it will swell from a smudge into a magnificent spiral filling the heavens. Its stars will no longer be distant. They will crowd into our sky, dazzling us with rivers of light. And then the collision will begin. What happens when two giants collide? We imagine chaos, destruction, stars smashing into stars. But here is the first strange truth. The galaxies are so spacious, the distances between stars so immense, that direct collisions between suns will be rare. If our solar system survives, it may drift through the merging galaxies untouched, like a small boat carried by an incoming tide. The true drama lies not in stars hitting stars, but in the slow reshaping of gravity itself. As Andromeda approaches, the Milky Way's delicate spiral arms will warp and twist. Stars will be tugged from their orbits, flung into vast streams that stretch across the sky. Some will be hurled into intergalactic space, banished forever from any galaxy. Others will be drawn inward, toward the deepening gravitational wells of the two central black holes. Imagine the night sky filled with long arcs of stars, curving rivers of light stretching from horizon to horizon. That is the beauty of galactic collision, destruction painted as art. And then comes the center. At the heart of the Milky Way lies Sagittarius A*, a black hole 4 million times the mass of the Sunday. At the heart of Andromeda lies a black hole at least 100 million solar masses. When the galaxies merge, these two monsters will spiral toward each other. Slowly at first, then with increasing fury, they will draw closer, emitting invisible ripples of gravity that race across the universe. Finally, in a moment of unimaginable power, they will merge into one supermassive black hole, shaking the very fabric of space-time. What if humanity is still here to see it? What would it mean to look up at the sky and witness another galaxy filling the heavens? Imagine standing on Earth as Andromeda's spiral arms stretch across half the sky, brighter than the Milky Way has ever appeared. Imagine watching new stars ignite in bursts of light as clouds of gas collide and compress. Imagine knowing that every night is history unfolding, the sky itself alive with transformation. This collision will not be quick. It will take billions of years. The first encounter will pull the galaxies apart, stretching them into strange shapes. Then gravity will draw them back together. They will pass through each other, separate, and return again, locked in a gravitational dance. Eventually, after several passes, they will merge completely. The result will not be a spiral galaxy at all, but a vast elliptical galaxy, a swollen, glowing orb of stars, its spirals erased by the violence of the union. Astronomers already have a name for this future creation, Milkomeda. But even Milkomeda will not be the end of the story. The local group of galaxies contains dozens of dwarfs orbiting both the Milky Way and Andromeda. When the giants collide, many of these smaller galaxies will be swallowed as well. The result will be a single, enormous galactic empire, stretching farther and glowing brighter than either of its parents. A colossus born from collision. Here is where the mystery deepens. If galactic collisions are so inevitable, why is the universe not filled with ellipticals? Why do we still see so many spirals? The answer lies in time. Collisions take billions of years to unfold. What we see now are galaxies frozen in their present forms, snapshots of a universe still in motion. But given enough time, most spirals will eventually merge, leaving behind a cosmos dominated by giant elliptical galaxies. The Milky Way and Andromeda are simply next in line. And yet, for us, there is something strangely intimate about this future. We live in the quiet before the storm. For the moment, Andromeda appears fragile, delicate, like a smudge barely clinging to the night. But that faintness hides inevitability. The collision has already begun, not in starlight, but in the invisible halos of dark matter that already overlap. The dance is underway. We are living inside its opening steps. What if our descendants survive to witness it? What if civilizations billions of years from now stand beneath the sky of the future Earth, or whatever world humanity inhabits, and watch as two galaxies become one? They will see things we can barely imagine. Ribbons of stars stretching across the night, supernovae bursting in great chains, black holes merging with such force that even the structure of time will shudder. They will not need to imagine paradise or apocalypse. They will see both written in the stars. But what if humanity does not endure that long? The beauty of this prophecy is that it exists whether we are here or not. The cosmos will dance its steps with or without us. The galaxies will merge. The black holes will unite. The streams of stars will arc across the heavens. Our presence, or absence, is irrelevant to the outcome. And yet, knowing this, we feel something profound. Because for now, we are here. For now, we are the ones who know the prophecy. We are the ones who can look at Andromeda tonight and whisper, "You are coming." Andromeda is not just the largest galaxy in our skies. It is the most important story of our future. Its collision with the Milky Way will shape the destiny of every star, every planet, every orbit in our local group. Our sun may survive, drifting into a new orbit within Milkomeda, or it may be flung outward, exiled to the galaxy's edge. Earth may continue circling its star, its sky forever transformed, or Earth may be cast adrift into intergalactic space, a wandering world under the cold night. The dice have already been thrown. The outcome is only a matter of waiting. Think of the poetry of it. The faint blur in tonight's sky, so fragile to the naked eye, is the very thing that will one day dominate our heavens. The quiet neighbor is, in fact, the storm on the horizon. The colossus next door is not merely larger than we imagined, it is the architect of our future. And so the question deepens. If the Milky Way and Andromeda are already destined to merge, what other hidden forces shape our destiny? What invisible tides guide the galaxies themselves? The collision is not only about size or gravity, it is about the very architecture of the universe, the scaffolding of dark matter, the relentless pull of cosmic expansion. The dance of galaxies is written into the fabric of reality itself. And this brings us to our next step. To understand what will truly happen when giants collide, we must look beyond the visible. We must confront the mystery of dark matter, the hidden mass that makes these collisions possible, and the unseen hand that binds galaxies into the cosmic web. Part 4. The Dark Web of Andromeda. If Andromeda is the colossus next door, then its true body is not what we see, but what we cannot. The luminous spiral, the trillion stars, the glowing clouds, all of this is decoration, surface, skin. The real Andromeda, the true Andromeda, is something darker, something invisible, something we can only know through the way it pulls on everything else. Astronomers call it dark matter, but the word is misleading. It is not dark the way a shadow is dark. It does not glow, but neither does it block light. It is not dust, not smoke, not some cosmic fog. It is matter we cannot touch, cannot see, cannot hold in our hands, and yet it outweighs everything we know. The first clue came from motion. When astronomers measured how fast Andromeda's stars orbit around its center, they expected the outer stars to move more slowly than the inner ones, the way planets slow down as they orbit farther from the Sunday. But in Andromeda, something impossible appeared. The stars on the edges were moving just as fast as those near the core. They should have flown off into intergalactic space, yet they did not. Something invisible was binding them, something heavy, immense, unseen. That something is dark matter. It forms a halo around Andromeda, a vast, spherical cloud that may stretch nearly 1,000,000 light-years across. Imagine a sphere so large that it reaches almost halfway to the Milky Way, an invisible ocean of gravity, wrapping Andromeda like a cloak. This halo contains more mass than all of Andromeda's stars combined. If the luminous galaxy is the tip of the iceberg, then dark matter is the mountain beneath the sea. And here is the unsettling part. The halo of Andromeda already overlaps with our own. The Milky Way, too, is wrapped in dark matter. The two invisible oceans touch. They may even interpenetrate, streams of unseen particles drifting through one another in silence. This means the collision between our galaxies has already begun, not with stars, not with light, but with darkness. What if we could see it? If our eyes were sensitive to dark matter, the night sky would not look like a field of pinpoints. It would look like a vast web, strands of invisible substance stretching across the universe, connecting galaxies like beads on a string. Astronomers call this the cosmic web. Andromeda is not floating alone. It is caught in this web, pinned in place by filaments of dark matter that extend across millions of light years. The cosmic web is not just structure, it is destiny. It is the framework that dictates where galaxies form, how they grow, how they collide. Without dark matter, there would be no Andromeda, no Milky Way, no stars, no planets, no life. Everything we know is built on the scaffolding of something we cannot see. But what is it? That is the question that has haunted physics for decades. Some say dark matter is made of weakly interacting particles, WIMPs, ghostly entities that pass through ordinary matter as if it weren't there. Trillions may flow through your body every second, unnoticed, unresisted. Others say it may be axions, ultra-light particles that ripple through the universe like waves. Still others imagine primordial black holes, tiny relics from the birth of the cosmos, scattered invisibly through space. The truth is, we do not know. Andromeda's size is the evidence, but the culprit remains hidden. We see the way it bends the orbits of stars, the way it pulls on dwarf galaxies, the way it warps light from background quasars through gravitational lensing. But the substance itself eludes us. Imagine standing on a beach, watching waves lap the shore. You cannot see the wind, but you know it exists because you see the waves it drives. Dark matter is like that wind, invisible, intangible, yet undeniable. And Andromeda is one of the most powerful demonstrations of its presence. What if we lived in a universe without it? The outer stars of Andromeda would drift away. Its spiral arms would unravel. Our Milky Way would never have held together. The sky itself would be empty, scattered, barren. We owe our existence to this hidden matter. We are children not only of stars, but of shadows. And here lies a deeper mystery. If dark matter shapes galaxies, then what does it mean for two halos to merge? When Andromeda and the Milky Way finally collide, their stars may pass each other peacefully, but their halos will not. They will crash, mix, and settle into one giant ocean of invisible gravity. It will be the halos, not the stars, that decide the final shape of Milkomeda. The unseen will sculpt the visible. The dark will determine the light. This is why the more we study Andromeda, the stranger it becomes. The visible spiral is a mask. The true galaxy is a vast, dark sphere, heavy beyond comprehension. We think of ourselves as living in a spiral galaxy, but in reality, we live in a shadow, wrapped in a halo that dwarfs the light. And so does Andromeda. What if dark matter is not only matter? What if it is also message? Some theorists have dared to suggest that dark matter could carry information, that it may have properties we have not yet imagined. Could civilizations, advanced beyond us by millions of years, have learned to harness it, to ride its currents the way we ride the winds? Could Andromeda's halo conceal not only mass, but meaning? We do not know, but the possibility lingers like a whisper. Every time astronomers refine Andromeda's mass, the numbers rise. Every time they map its halo, the boundaries expand. It is as if the galaxy resists being pinned down, as if it wants to remind us that the most important things in the universe are not what we see, but what we cannot. And so we return to the question, what is Andromeda's true size? Do we measure the spiral arms, glowing with 1 trillion stars? Do we measure the faint streams of cannibalized galaxies curving across its outskirts? Or do we measure the invisible halo, 1 million light-years wide, overlapping with our own? The answer is all of these. The answer is that Andromeda's true body is far larger than its visible self. Tonight, as you drift toward sleep, imagine the sky not with stars alone, but with the web beneath. Imagine invisible strands of dark matter stretching across the cosmos, binding galaxies together like beads on a thread. Imagine Andromeda not as a blur, but as a vast, unseen hand already pressing against the Milky Way. Imagine that you live not in empty space, but in a hidden ocean of shadow, one that flows through your body every second, unnoticed, untouchable, yet essential. This is Andromeda's true nature. The Colossus is not only light, it is darkness, a darkness without which there would be no stars at all. And yet, even this is not the end of the mystery. For if dark matter holds Andromeda together, another force is pushing the universe apart, a force even stranger, even more elusive: dark energy. To understand Andromeda fully, we must look not only at what holds it, but at what seeks to scatter it. That will be the next chapter in our journey. Part 5: Andromeda and the Silent Force. There is another force at work in the universe, one that is not pulling us inward, but pushing us apart. One that whispers not of gravity and closeness, but of distance and emptiness. Astronomers call it dark energy, and though it is silent and invisible, it may be the most powerful influence in the cosmos. To understand Andromeda, to truly understand what it means that our galaxies are fated to collide, we must also consider this force that works against collision. Dark matter pulls together, dark energy pushes apart. Between them, the universe is balanced like a ship tossed on invisible tides. The story of dark energy begins with something simple: the expansion of the universe. For decades, astronomers believed the expansion, born in the Big Bang, should be slowing down. Gravity, the pull of galaxies on one another, ought to resist expansion. The universe should grow, yes, but more slowly with time. But in the late 1990 seconds, astronomers discovered something shocking. By measuring distant supernovae, exploding stars that serve as standard candles, they found that the universe was not slowing down. It was speeding up. The expansion was accelerating. Some mysterious energy was pushing galaxies apart faster and faster, as though the very fabric of space itself were stretching with increasing urgency. This force is what we call dark energy, and though we cannot see it, we know it exists because of its effect: the accelerating expansion of the universe. According to our best estimates, dark energy makes up about 70% of all the energy in the cosmos. Dark matter is about 25%. Ordinary matter, everything we see, from stars to planets to ourselves, makes up less than 5%. Pause for a moment. That means everything we know, everything we can touch and see, is only a sliver of reality. The rest is shadow and silence, dark matter binding, dark energy pushing. What does this mean for Andromeda? At first glance, it seems strange. If dark energy is pushing galaxies apart, why are the Milky Way and Andromeda on a collision course? Shouldn't they be drifting away, lost in the accelerating tide? The answer is gravity. On the scale of the local group, gravity wins. Andromeda is close enough, only 2.5 million light-years away, that the gravitational pull between it and the Milky Way overcomes the push of dark energy. The local group is a kind of island, bound together, even as the greater universe expands around it. Inside the island, gravity rules. Outside, dark energy reigns. But what if we look farther ahead? After Andromeda and the Milky Way merge into Milkomeda, the universe will continue to expand. Over billions of years, galaxies beyond our local group will accelerate away from us, faster and faster, until their light can no longer reach us. The cosmic horizon will shrink. The night sky will grow emptier. Milkomeda will be surrounded not by countless galaxies, but by silence. The rest of the universe will drift out of view. This is the paradox of Andromeda. On the one hand, it is the galaxy that will collide with us, reshaping our destiny in a cosmic dance. On the other hand, it is also one of the last galaxies we will ever see. As dark energy carries the rest of the cosmos away, Andromeda remains. Its light is a promise that we will not be alone, even as the universe grows cold and distant. But what is dark energy? Here, the mystery deepens. Some call it a property of space itself, a cosmological constant, first suggested by Einstein. In this view, empty space is not truly empty. It has energy, and that energy pushes space apart. Others suggest it may be something dynamic, a field that changes over time, waxing and waning with the history of the cosmos. Still others wonder if our understanding of gravity itself is incomplete, and that dark energy is not a thing at all, but a sign that the laws we trust may be flawed. What if dark energy is not uniform? What if it varies across the universe, stronger in some places, weaker in others? Could this explain the puzzles we see, the tensions in measuring the Hubble constant, the strange cold spots in the cosmic microwave background? What if Andromeda itself is caught in a subtle difference of expansion, drawn toward us not only by gravity, but sheltered from dark energy's push by the overlapping halos of our galaxies? There is something almost poetic in this. The faint blur in our sky, so fragile to our eyes, may be the only reason we will not be left utterly alone in an accelerating cosmos. Andromeda is not just our neighbor, it is our companion against the silence. Imagine, billions of years from now, civilizations in Andromeda looking out at the night sky. They will see stars, yes, they will see clusters within their own galaxy, but beyond, nothing. The rest of the universe will have slipped beyond the horizon, carried away by dark energy faster than light itself can cross the gulf. To them, the cosmos will appear empty. They will not know there are other galaxies. They will not know of the great web beyond. Unless they dig into the fossil light of the past, the ancient radiation left over from the Big Bang, they will never know the true vastness. And we live in the brief era when the truth is visible. We can still see Andromeda. We can still see galaxies billions of light years away. We can still measure the acceleration and whisper, something is pushing, something vast, something silent. And here is the most haunting thought. Dark energy may not be constant. It may grow stronger with time. If it does, the universe faces a fate more violent than mere emptiness. Some scientists call it the Big Rip. In this scenario, dark energy increases until it tears galaxies apart. Stars are ripped from galaxies, planets are ripped from stars. Even atoms themselves are torn asunder by the accelerating expansion of space. If this is true, then not even Andromeda will survive forever. But what if dark energy is not an end, but a cycle? Some theories suggest the universe expands, then collapses, then expands again, an eternal rhythm of birth and death. What if dark energy is simply one note in that rhythm, a passing phase before the cosmos resets itself? If so, Andromeda's collision with the Milky Way may be one small act in an infinite play, repeated across cycles without number. The silence of dark energy is unsettling, but it is also strangely comforting, because it reminds us of how precious this moment is. We are alive in a time when we can see the universe in its fullness. We can see Andromeda. We can see the galaxies beyond. We can measure the acceleration, weigh the halos, trace the web. Billions of years from now, none of this will be possible. The skies will be quiet. The cosmos will seem empty. But we are here, now, in the brief window when the truth is visible. Andromeda, then, is not only a colossus, it is also a reminder that the universe is vast, that unseen forces shape our destiny, that what we see is only a fraction of what is. It is a companion in light and in darkness. As you drift deeper into this night, imagine the forces at play. Gravity pulling, dark energy pushing. Imagine our galaxy and Andromeda locked together, their halos overlapping, their fates intertwined, even as the wider universe slips away. Imagine the silence of dark energy spreading across space, carrying galaxies beyond sight, even as we and Andromeda move closer. Imagine how strange, how paradoxical, how beautiful it is that in a universe of expansion, we are destined for collision. And here lies the deeper question. If dark energy shapes the future of the universe, what role does it play in the birth of galaxies themselves? Could it be that Andromeda's size, its immensity, is not only the result of dark matter's pull, but also dark energy's push? Could the balance of these two unseen forces explain why Andromeda is the largest spiral in our skies? This is the mystery we now approach. The unseen hand of dark energy may not only dictate the universe's fate, but also Andromeda's present. To unravel this, we must return to the earliest times, when galaxies first formed, and see how expansion, gravity, and shadow worked together to shape the giants we see today. Part 6. The Birth of Giants. Every colossus has an origin story. Every giant, no matter how vast, began as something small, and so it is with Andromeda, the greatest spiral in our skies. Tonight, let us travel backward far beyond the age of our planet, beyond the birth of the sun, beyond even the first galaxies until we arrive at the moment when Andromeda itself began. The universe was young then. Only a few 100 million years had passed since the Big Bang. The cosmos was still dark, a sea of hydrogen and helium gas, cooling from the furnace of creation. There were no galaxies yet, no stars to light the sky, just a fog of potential, waiting for gravity to sculpt it. And then the first sparks appeared. Dense knots of matter collapsed, igniting the earliest stars, enormous, unstable giants that burned hot and died young. Their explosions seeded the gas around them with heavier elements, iron and carbon, oxygen and nitrogen, the raw ingredients for future worlds. These first stars were brief torches, but they lit the way for galaxies. Andromeda was born from these early torches, not in a single instant, but through a slow gathering of clouds and clusters. Gravity pulled gas together, forming the first small galaxies. Those small galaxies collided and merged, building something larger. Over hundreds of millions of years, Andromeda grew not as a solitary creation, but as a patchwork, stitched together from the bones of smaller systems. Astronomers believe Andromeda began as a swarm of dwarf galaxies, tiny collections of stars orbiting within halos of dark matter. Each one, on its own, was fragile, but together, under the pull of gravity, they fell inward, combining their light into something greater. The Andromeda we see today is the child of 1,000 ancestors, and the evidence is still there. Across Andromeda's halo stretch faint streams of stars, tidal rivers, remnants of ancient collisions. These streams are fossils, each one a signature of a smaller galaxy torn apart and absorbed. To study them is to read Andromeda's history written in starlight. One stream traces back 6 billion years, another dates to only 2 billion, and each tells the same story. Andromeda has always been hungry. But hunger alone does not make a giant. Something else shaped Andromeda's rise: its environment. Our local group of galaxies is not empty. It is part of a larger structure called the Virgo supercluster, itself a thread in the cosmic web. Along this web, galaxies do not form randomly. They gather at intersections where filaments of dark matter cross. Andromeda grew at such a crossroads. Rivers of gas flowed along the filaments, feeding it. Smaller galaxies drifted down those same streams, delivering fresh stars and material. The location was perfect, a fertile valley in the universe's landscape, where everything it needed arrived on invisible highways of dark matter. Some astronomers believe Andromeda's mass owes much to a single, ancient merger. Billions of years ago, it may have collided with another large galaxy, perhaps equal in size. That violent union could explain why Andromeda is larger than the Milky Way, why its bulge is swollen with older stars, and why its halo stretches so absurdly far. If true, then Andromeda is not only the product of many small meals, but of one colossal feast. Picture that moment: two great spirals approaching, their arms distorted by gravity, their gas clouds crashing together. For hundreds of millions of years they danced, passing through one another, separating, then colliding again. Each encounter tore away stars, ignited bursts of star formation, and swelled the galaxy's black holes. When at last they merged, what emerged was not a ruin but a greater spiral, the ancestor of the Andromeda we see tonight. And yet, the story of Andromeda's birth is not just about mass and mergers. It is about chemistry. The earliest stars in Andromeda were poor in metals, astronomers' term for anything heavier than helium. But as generations of stars lived and died, they enriched the galaxy's gas: carbon for life, oxygen for air, iron for blood, all of it forged in Andromeda's furnaces. Each supernova scattered elements into the galactic medium, seeding clouds that would form new stars and planets. If life ever arises in Andromeda, it will owe its existence to these ancient cycles. In a sense, Andromeda has been preparing the ingredients of life for billions of years. Think of that. While Earth was still molten rock, Andromeda was already creating the chemical alphabet of biology. By the time our Sun formed 4.5 billion years ago, Andromeda had already experienced countless cycles of starbirth and death. It was already ancient. It was already vast. And yet, even as it grew, Andromeda was never isolated. Its satellites followed it like children around a parent. Today, over 30 dwarf galaxies orbit Andromeda, the most famous being M32 and M110. These satellites are not bystanders, they are witnesses. Their motions reveal Andromeda's mass. Their histories reveal its past. Some show scars of encounters, hints that they too may one day be absorbed. They are pieces of the same story, fragments of the same symphony. But here lies the deepest mystery. Why did Andromeda grow so much larger than the Milky Way? We share the same cosmic neighborhood. We were born in the same epoch. We were fed by similar rivers of gas. And yet Andromeda became the largest spiral in the local group. The answer may lie in chance. A single major merger billions of years ago could have given it an advantage, tipping the balance of growth. Or perhaps its position within the cosmic web was more favorable, its filaments richer in gas. Or perhaps the Milky Way is not as quiet as it seems. Perhaps we too had a colossal merger, and our scars have simply faded more completely. But what if there is another answer? What if Andromeda is not simply the product of chance, but of deeper laws? What if the universe itself prefers giants? Some cosmologists suspect that galaxies above a certain size may be self-reinforcing. The bigger they are, the more gas they attract, the more satellites they absorb, the more rapidly they grow. Growth begets growth, and Andromeda is the proof. Whatever the cause, the result is undeniable. Tonight, when you gaze at that faint blur, you are looking at the child of countless collisions, the heir of a billion stars, the giant born from rivers of gas and webs of dark matter. You are looking at a galaxy that has been growing for over 10 billion years. Andromeda's story is not one of peace, but of persistence. It has endured explosions, collisions, cannibalism, chaos, and yet it thrives. It is the greatest spiral we know, the ruler of the local group. And still, the story is unfinished. For every birth implies a death, every growth implies an ending. If Andromeda was born from collisions, then it will also end in one, and that ending will not be gentle. We have already glimpsed it, the inevitable collision with the Milky Way. But before we face that destiny, we must ask another question. If Andromeda was born from giants, what secrets lie hidden in its heart? What is the nature of its central black hole? What does it mean that such a massive object sits at its core, unseen, shaping everything around it? That is where our journey leads next. Into the shadows at Andromeda's center, into the gravitational abyss from which no light escapes. Part 7. The Monster in the Heart. Every galaxy has a secret. At its center, hidden behind veils of stars and dust, lies a darkness deeper than night. A singularity, a well of gravity so fierce that not even light can escape. Andromeda is no exception. For all its trillion stars and radiant arms, its true ruler is invisible, a supermassive black hole more than 100 million times the mass of our Sunday. Let us pause on that number. 100 million suns, compressed into a region smaller than our solar system. Imagine the weight of it, the impossible density. Imagine a sphere of gravity so strong that space itself curves inward, trapping everything that dares to cross its boundary. This is the monster at the heart of Andromeda. But the monster is silent. Unlike some black holes that blaze with torrents of energy as they devour matter, Andromeda's central black hole slumbers. It is not dead, but sleeping. Gas falls toward it slowly. The glow is faint. To our telescopes, it is a shadowy core, quiet compared to the raging beacons we call quasars. Yet silence does not mean weakness. Even in its dormancy, its gravity shapes the orbits of stars tens of thousands of light years away. Even in its quiet, it dictates the life of the galaxy. How did such a monster form? There are several stories scientists tell. One is that long ago, in the young universe, massive stars collapsed, leaving behind black holes that merged and grew. Over billions of years, they consumed gas, swallowed stars, and grew into titans. Another possibility is more dramatic, that black holes may have formed directly from vast clouds of gas, collapsing under their own weight without ever becoming stars. If so, Andromeda's monster may be as old as the galaxy itself. There is evidence that Andromeda's black hole once shone more fiercely. In its youth, it may have been an active nucleus, blazing like a quasar, outshining the entire galaxy around it. We see scars of that past, shells of gas, subtle structures near the core, hints that once upon a time it fed greedily. What would that have looked like billions of years ago? Imagine the night sky of a distant Andromedan world. Above its horizon, a starless black sun, blazing brighter than all other stars combined, hurling jets of radiation into space. It would have been terrifying, and yet it was that fury that helped shape the galaxy, regulating star formation, sculpting the flow of gas, deciding which regions birthed stars and which remained barren. The black hole is not simply a parasite, it is also an architect. Without it, Andromeda would not be the galaxy we know. Without its gravitational command, the dance of stars would lose coherence. The center holds because the monster holds it, and this brings us to a haunting thought. In about 4 billion years, Andromeda's black hole will meet our own. Sagittarius A*, the Milky Way's central black hole, is smaller only 4 million solar masses compared to Andromeda's 100 million. When the galaxies collide, their central holes will circle each other, spiraling inward, sending ripples of gravitational waves across the universe. At last they will merge, forming one black hole of unimaginable size. That collision will be invisible to the eye, but not to space-time itself. The universe will shudder. But even before that final union, the monster influences us. The Milky Way and Andromeda are bound by their halos, yes, but the deeper truth is that both galaxies are ruled from the core. These black holes are like captains steering titanic ships, invisible but decisive. When they merge, it will not simply be a collision of galaxies, it will be the fusion of two ancient rulers. What if these black holes hold more than mass? What if they store memory? Every star that falls in, every gas cloud that disappears, adds to the singularity. What if, deep inside, there is a record of all that was consumed? Not accessible, not retrievable, but present in some unimaginable way. Could Andromeda's black hole contain within its event horizon the story of a billion stars, the whispers of galaxies it has devoured? Some scientists have even speculated that black holes might be gateways, portals to other universes, bridges to dimensions beyond our own. We do not know. All we know is that, at the heart of Andromeda, lies a mystery deeper than any telescope can see. Andromeda's black hole is not alone. It is surrounded by a dense cluster of stars, a nuclear star cluster, glowing faintly around the abyss. These stars orbit at fantastic speeds, racing around the black hole like sparks around a furnace. Their orbits tell us the black hole's mass, for only such an immense gravitational anchor could hold them in check. It is like watching leaves swirl in a whirlpool and deducing the strength of the water. From the dance of stars, we measure the darkness, and the darkness grows. Slowly, invisibly, the black hole feeds. Every star that wanders too close, every gas cloud that drifts inward, every fragment of dust, it all adds to the mass. Over billions of years, the monster has grown from something small into something colossal, and it will not stop. In time, after the merger with the Milky Way, it will become larger still. Here is the paradox. Black holes are destruction, and yet they create. Without them, galaxies would not be galaxies. Without them, stars would not cluster, gas would not settle, structure would not hold. They are monsters, yes, but monsters upon which the cosmos depends. Imagine Andromeda without its heart. The spiral arms might unravel, the bulge might disperse, the orbits might dissolve. The beauty we see would fade into chaos. The black hole is the unseen conductor of the galactic symphony, silent but essential. And yet, we are left with unease. What lies beyond the event horizon? The mathematics tells us a singularity, a point of infinite density where space and time collapse. But infinities are not answers, they are warnings. They tell us that our physics, as elegant as it seems, is incomplete. Andromeda's heart may conceal not just mass, but new laws of nature, truths waiting to be discovered. What if the black hole is not a prison, but a seed? Some theories suggest that every black hole may give birth to a new universe, a bubble of space-time budding off from ours. If so, Andromeda's core may already contain countless infant universes, inaccessible to us, yet real. What if the monster in the heart is also a mother? We cannot know. We can only wonder. Tonight, as you lie in the quiet, think of that faint blur above the horizon. Within it lies a darkness greater than we can comprehend. A black hole 100 million times the sun, silent now but once blazing like a quasar, and destined one day to merge with our own. It is the most hidden, most powerful, most mysterious part of the nearest giant galaxy, and this is only one chapter of its story, because Andromeda's heart does not exist in isolation. It lives within a galaxy that continues to grow, to feed, to change. Streams of stars, remnants of galaxies already consumed, continue to fall toward it. And in those streams lies another truth. Andromeda is not finished. It is still building itself. It is still hungry. To understand Andromeda fully, we must follow those streams. We must trace the remnants of the galaxies it has already devoured, for only then can we see not just its heart, but its appetite. Part 8. Rivers of Stars. Andromeda is not a peaceful neighbor. It is not merely a silent spiral hanging in the sky. Look closely, and you will see scars. Long, faint ribbons of light stretch across its halo, curving like rivers frozen in time. These are not random decorations. They are the remains of galaxies, torn apart and swallowed. Andromeda is a cannibal. Astronomers discovered this truth by mapping faint stars at the galaxy's edges. Instead of finding an even distribution, they saw arcs and streams, glowing trails that loop around the core. Each stream is a relic, the remains of a smaller galaxy that wandered too close. Gravity pulled it apart, star by star, until what was once whole became a river of fragments. These rivers now circle Andromeda, testimonies to a hunger that has lasted billions of years. Think of the poetry of it. A galaxy, majestic and serene from a distance, is up close a battlefield. Behind the beauty of spiral arms lies violence. Behind the glow of starlight lies conquest. Andromeda did not grow to its colossal size by accident. It grew by devouring others. One of the most dramatic examples is the giant stellar stream, a ribbon of stars stretching hundreds of thousands of light years across Andromeda's halo. It is the shredded remains of a galaxy consumed perhaps 2 billion years ago. Even now, its stars continue to rain down, falling into Andromeda's heart. If you could stand within that stream, you would see a night sky unlike any other dense with stars, brighter than the Milky Way's core, all flowing in the same direction, all caught in the gravity of a giant. And this stream is not alone. Dozens of smaller rivers weave through Andromeda's outskirts. Some are older, their galaxies consumed so long ago that only faint echoes remain. Others are recent, sharp and bright, the wounds of a fresh collision. Together, they tell a single story. Andromeda's history is written in cannibalism. The Milky Way, too, is a cannibal. Our own halo contains the remains of smaller galaxies we have and absorbed. The Sagittarius dwarf galaxy is being torn apart even now, its stars forming streams across our sky. But Andromeda's appetite is greater. Its streams are larger, more numerous, more violent. If the Milky Way is a hunter, Andromeda is a predator on another scale. Why does this happen? Why do giants consume the small? The answer is gravity, relentless and merciless. Small galaxies orbit large ones, and over billions of years, their orbits decay. Tidal forces tear them apart, stretching them into streams. Eventually, their stars scatter, blending into the larger galaxy. It is not cruelty, it is simply the law of the cosmos. The strong grow stronger by absorbing the weak. But what if there is more? What if these streams are not just remnants, but clues to Andromeda's future? Each stream reveals the shape of the dark matter halo, for stars follow invisible currents. By studying them, astronomers map the unseen structure that binds the galaxy. The rivers of stars are tracers of the invisible web. In their curves and arcs lies the fingerprint of Andromeda's dark skeleton. There is a haunting symmetry in this. What was once a galaxy, vibrant and alive, becomes a tool for measuring another's size. Its destruction becomes data. Its death becomes knowledge. Andromeda's cannibalism raises another question. How many galaxies has it already consumed? The answer may be dozens. Some scientists suggest that much of its mass, perhaps half, came from ancient mergers. Every one of its trillion stars may once have belonged to a smaller system. And yet, when we look at Andromeda tonight, we see only a single, unified spiral. The evidence of violence is hidden, blurred by time. Only faint streams remain, like ghostly rivers in the dark. Imagine standing on a planet inside one of those doomed galaxies, billions of years ago. At first, the night sky would have seemed normal. Stars above, nebulae glowing. Then, slowly, Andromeda would grow brighter. Night after night, it would swell, filling more of the heavens. until one day, its arms would dominate the sky, brighter than any moon. Tides of stars would stretch across space, tearing your galaxy apart, and in time, your world would no longer orbit its own galaxy, but Andromeda's vast center. The predator would have claimed you, and this is our future too. For in 4 billion years, the Milky Way will become another stream, another river feeding Andromeda's hunger. The collision will not be gentle. Our stars will stretch into arcs, our spiral will unravel, and at last, our galaxy will be absorbed into the giant. In the distant future, perhaps on some alien world orbiting a star in the merged Milkomeda, astronomers will study faint streams across the halo and whisper, "This was the Milky Way." But even then, the cycle will not end. For cannibalism is not a phase, it is the nature of galaxies. Every galaxy grows this way. Collisions are the lifeblood of cosmic evolution. Without them, galaxies would remain small, unable to ignite great bursts of star formation. Without them, there would be no giants like Andromeda. And so we are left with a paradox. Destruction creates beauty. Violence creates light. When galaxies collide, clouds of gas compress, birthing new stars. Death feeds life. The predator gives rise to creation. Andromeda is not only a destroyer, it is also a mother. The stars born from its collisions will shine for billions of years, lighting the darkness long after the memories of those cannibalized galaxies have faded. What if this cycle is universal? What if every giant we see across the sky is the product of endless cannibalism? Every stream of starlight a remnant of something lost? What if the cosmos itself is not a calm expanse, but a battlefield, where creation and destruction are forever entwined? Tonight, as you drift deeper into stillness, imagine those rivers of stars flowing through Andromeda's halo. Imagine each one as a ghost, a memory of a galaxy that once was. Imagine how strange it is that we, tiny beings on a small planet, can see them at all. From across 2.5 million light-years, we can detect the faint glow of cannibalism, the scars of battles fought billions of years ago. We are witnesses to a history written not in words, but in streams of light across the sky. And here is the haunting part. The process has not stopped. Even now, Andromeda continues to feed. Its satellites M32, M110, and many smaller dwarfs are being drawn inward, their orbits decaying, their stars already feeling the tug. In time, they too will unravel, becoming streams in the halo. The feast is ongoing, the hunger is eternal. So, when we say Andromeda is the most massive galaxy in our local group, remember this. Its greatness was built on consumption. Its beauty was carved from destruction. The colossus next door is also the predator next door. And this truth leads us into a deeper mystery. For if Andromeda has consumed so many galaxies, then its core must bear the weight of those meals. Its black hole must have grown by feeding not only on stars, but on the central black holes of its victims. And that raises a profound question. What happens when black holes merge inside a cannibal galaxy? What forces are unleashed when monsters eat monsters? That is where our journey turns next. Part 9. When monsters feast, every collision leaves scars. Every act of cannibalism carries consequences. And when galaxies merge, their brightest scars do not lie in their streams of stars, but in the hearts of the galaxies themselves. For at the center of every galaxy lurks a black hole. And when galaxies are devoured, those black holes do not vanish. They survive. They are drawn together. They merge. Andromeda has done this before. It is not speculation. It is written in its mass. Its central black hole, weighing over 100 million suns, is far too large to have grown only by swallowing gas and the occasional star. To reach such immensity, it must have consumed other black holes, which means that Andromeda has not merely eaten galaxies, it has eaten the monsters at their hearts. Imagine that. A black hole, itself already the most extreme object in the universe, drawn toward another, spiraling closer, pulled by gravity into an embrace that no force can resist. Around them, stars whirl chaotically, gases shredded, heated to millions of degrees, flaring in X-rays. Invisible ripples of gravity race outward at the speed of light, carrying news of the merger across the cosmos. And then, in the silence of the event horizon, the two become one. Mass is added to mass. A greater monster is born. This is the hidden history of Andromeda. We see its size, its halo, its rivers of cannibalized stars. But buried in that history are deeper events, titanic black hole mergers, each one a catastrophe beyond comprehension, each one adding weight to the colossus we see today. How many such mergers has Andromeda endured? We cannot yet know. But every stream in its halo, every devoured galaxy, was likely accompanied by a smaller black hole spiraling into its center. One by one, over billions of years, those black holes joined the growing giant. Each merger released more energy and gravitational waves than all the stars in the universe shining together. And yet we did not hear it. We were not there. The waves passed silently through the cosmos, through Earth itself, through us, leaving only faint whispers for our detectors today. If we had been there, if humanity had existed in those times, the sky would have been transformed. The galaxy's core would have blazed with violence. Gas clouds falling inward would have lit up as quasars, brighter than all the stars of Andromeda combined. For millions of years, Andromeda may have shone as a cosmic beacon, visible across billions of light years. Civilizations in distant galaxies could have seen its light, could have whispered stories of a distant spiral ablaze with fury. And then the light would fade, the black holes would merge, the gas would settle, silence would return. The monster would be larger, but calm. Andromeda would continue its patient growth, waiting for the next feast. This cycle of violence and silence may have repeated countless times, each merger leaving the black hole larger, heavier, more dominant, each merger shaping the galaxy around it. This is how giants are made, not by one event, but by many, not by peace, but by devouring. And yet, there is something almost poetic in the inevitability. Black holes do not fight. They do not resist. They spiral together, bound by gravity, and merge as one. There is no choice, no escape, no alternative ending. Their union is destiny. What if this is the true law of the cosmos? That everything, in time, is drawn into union. Galaxies merge, black holes merge, stars collapse into singularities. The universe itself may one day merge into silence. Andromeda, then, is not only a predator, it is a prophet. Its history of black hole mergers is a glimpse of the future for us all. When the Milky Way collides with Andromeda, the same story will unfold. Our central black hole, Sagittarius A*, will be drawn toward Andromeda's giant. The smaller will spiral into the larger, losing energy through gravitational waves, circling faster and faster until they unite. The final burst of energy will ripple through the universe. Civilizations billions of light years away may detect it, long after Earth itself is gone. To them, it will be a cosmic bell tolling. Two giants have become one. And what of us? If humanity endures, if we are there to witness it, we will not see the merger directly. Black holes are invisible, but we will see the signs. We will see the core flare as gas falls inward. We will see jets of radiation piercing the sky. We will see stars flung from their orbits, streaking into the halo like sparks from a fire. And we will know that the heart of our new galaxy has changed forever. But here lies the deeper mystery. What happens inside? What happens when two singularities merge? Our equations tell us the result. A larger black hole, mass added to mass. But inside the event horizon, beyond the point of no return, our physics fails. Do singularities truly combine? Or do they create something stranger, something we cannot yet imagine? Could the merger of black holes be the birth of something new, perhaps even the seed of another universe? We do not know. We cannot know. But the possibility lingers like a whisper. Perhaps every black hole merger is a creation event, invisible to us but real. Perhaps Andromeda, in devouring galaxies and merging black holes, has already given birth to countless hidden universes, budding off from ours like unseen blossoms in the dark. Andromeda's history, then, is not just a story of destruction. It may also be a story of creation, hidden from our eyes, written in the invisible depths of its core. Tonight, as you drift into the rhythm of sleep, imagine this: a galaxy not of peace, but of hunger. A black hole not of silence, but of mergers. Imagine the moment when two monsters circle each other, spiraling inward, faster and faster, until space itself quakes. Imagine the final instant, when the universe shudders with their union, and then silence. A silence deeper than any night. A silence that holds within it the weight of 100 million suns. This is Andromeda's heart. This is the history it does not show in its spiral arms or its trillion stars. The beauty we see tonight is built on the feasts of monsters. And here lies the haunting thought. What if this is happening now? What if, deep within Andromeda's core, black holes are spiraling toward each other even as we speak, invisible to us, their final moments hidden behind the veil of distance? What if, as you listen to this story, gravitational waves are already crossing space, silent ripples from a merger millions of years ago, just now reaching Earth? The cosmos is vast, its timescales are beyond our comprehension. But every night, as Andromeda glows faintly in the sky, remember, its light is ancient, and its darkness is even older. Within it lies not just stars and gas, but the memory of monsters feasting on monsters, shaping the galaxy we see today. And this leads us to the next chapter. For if black holes shape galaxies from the inside, what about the structures that shape them from the outside? What about the great web of galaxies, the filaments of dark matter and light that connect Andromeda to the larger cosmos? To understand Andromeda fully, we must step back. We must see not only its heart, but its place in the cosmic web. Part 10. Threads of the Cosmic Web. Step back, step farther still. Let your imagination drift outward, away from Earth, away from the Milky Way, away even from Andromeda itself. Watch the spiral arms shrink to a blur, the halo fade to a mist, until the local group of galaxies is no more than a handful of points scattered in the dark. Now step farther, until you see what lies beyond. The universe does not scatter its galaxies like dust. It arranges them. It weaves them. The pattern is called the cosmic web. This is the largest structure we know, a tapestry stretching across billions of light years. It is not random. It is ordered. Galaxies cluster along vast filaments of dark matter, threads of invisible substance that span the cosmos. Where the filaments intersect, galaxies gather into clusters and superclusters. Where the filaments thin, voids open, vast deserts of emptiness, hundreds of millions of light years across, almost devoid of stars. Andromeda is part of this web. It does not drift alone, but is pinned like a bead on a cosmic string. Together with the Milky Way, Andromeda sits inside the local group, and the local group itself is woven into the Virgo supercluster, which in turn belongs to something even greater, the Laniakea supercluster. Over 100,000 galaxies bound together, stretched along filaments of dark matter, flowing like rivers in space. It is here, in this grand architecture, that Andromeda finds its true home. Think of the paradox. To our eyes, Andromeda looks like an isolated blur, floating in the night sky. But in reality, it is part of a network vaster than anything we can imagine. Each filament of the cosmic web contains countless galaxies. Each intersection glows with clusters richer than anything in our local group. The web is not visible to the naked eye, but we can trace it through gravitational lensing, through the cosmic microwave background, through the distribution of galaxies across billions of light years. And everywhere we look, the same pattern appears. Threads, nodes, voids, a structure that is not chaos, but order. Andromeda is one of those nodes. What does this mean for its destiny? It means Andromeda is not just colliding with the Milky Way by chance. Their meeting was written into the web itself. From the moment the first clouds of gas collapsed, their filaments were guiding them, pulling them together, shaping their orbits over billions of years. The cosmic web is the stage, and galaxies are its actors. The script is gravity. The plot is inevitable. But here lies the unsettling truth. We do not know what the web is truly made of. We say it is dark matter. We say it is the invisible scaffolding of the universe. But what if it is something stranger? What if the web is not just matter, but information? What if galaxies are beads, not on threads of substance, but on threads of meaning? Pause and consider this. The pattern of the cosmic web resembles the neural structure of the human brain. Filaments of matter connect clusters of galaxies the way axons connect clusters of neurons. Some scientists have noticed this uncanny similarity. Is it coincidence, or is it hint? What if the universe itself is structured like a mind? What if Andromeda is not simply a galaxy on a thread, but a thought in a vast cosmic brain? We cannot answer these questions, but the resemblance lingers, haunting and profound. When we map the universe, we may be mapping something alive, something thinking. And if so, then Andromeda is not only our neighbor, it is also part of a thought larger than us, larger than any galaxy, larger than the cosmos itself. Even without such speculation, the cosmic web is astonishing. Imagine standing outside the universe, looking down on it as though it were a single object. You would not see scattered galaxies. You would see threads of light stretching across unimaginable distances, curving and branching, converging at brilliant nodes. You would see voids as black as silence, surrounded by walls of galaxies like luminous lace. You would see beauty on a scale so vast that the word infinite begins to tremble. And yet, despite its immensity, this web affects us directly. It is the web that delivered the rivers of gas that fed Andromeda. It is the web that guided the smaller galaxies into its halo. It is the web that set the stage for its cannibalism. Without the web, Andromeda would not be the giant it is. Without the web, there would be no local group, no Milky Way, no Earth. What if the web is still feeding us? Even now, streams of intergalactic gas flow along filaments, trickling into galaxies, replenishing their fuel for star formation. Andromeda, massive though it is not self-sufficient. It drinks from these cosmic rivers, just as our own galaxy does. The web is not just scaffolding, it is lifeblood. But the web also holds dangers, for galaxies do not remain forever in balance. Clusters collide, filaments shift. Gravity reshapes the pattern over billions of years. Already, the local group drifts toward the Virgo cluster, pulled by something larger still. The Great Attractor, a gravitational anomaly so immense it bends the motions of thousands of galaxies. Andromeda's future, and ours, is not only tied to each other, it is tied to forces farther out, woven into threads we cannot yet see. What if the cosmic web itself is unstable? What if dark energy, pushing galaxies apart, will one day tear the filaments themselves? Imagine the web unraveling, the threads snapping, galaxies cast adrift into eternal isolation. If that happens, Andromeda's grand destiny may end not in union with others, but in solitude. A giant trapped in silence, no longer fed, no longer connected, fading into the dark. The more we learn, the less we understand. That is the rhythm of the cosmos. The more we map the web, the more questions appear. Why does it look the way it does? Why do galaxies align along its threads? Why do we see echoes of its shape in our own neural networks? What if the universe is not only physical, but patterned with something deeper, something that repeats across scales, from atoms to galaxies to minds? Tonight, imagine this. You are floating far above the universe, looking down. You see the threads glowing, stretching across space like rivers of fire. You see Andromeda, a bead of light on one of those threads, already entangled with us. You see the Milky Way beside it, another bead, both sliding slowly toward one another along the same filament. Their collision, their merger, their future, all of it written into the geometry of the web. And then, imagine the silence, the voids between the threads, darker than any night you have known. If galaxies are cities of light, then these voids are deserts without end. To cross them would take billions of years. They are the true wilderness of the cosmos. And yet, without them, the web would not exist. The contrast between fullness and emptiness, light and dark, creates the pattern. The voids are as important as the filaments. Andromeda, then, is not only a galaxy, it is a note in a symphony. The cosmic web is the score. The music is gravity, dark matter, dark energy, and we tiny, fragile, brief our listeners. For the moment, we can hear the music. For the moment, we can see the web. For the moment, we can trace the threads. But this privilege will not last. Dark energy will carry distant galaxies away. The farther filaments will slip beyond our horizon. Billions of years from now, only the local group will remain visible. The rest of the web will vanish from view. Milkomeda will float in silence, surrounded by blackness. The map will fade, the music will end. And that is why this moment matters. We are alive in the era when the cosmic web is still visible. We can still trace the threads. We can still see Andromeda in its place, part of a pattern larger than imagination. We are the only species, as far as we know, that has looked up and recognized the web. That recognition is itself a miracle. And so we end this chapter with a question. If Andromeda is part of the web, what of its satellites? What of the dozens of smaller galaxies caught in its halo? Do they, too, reveal the threads of the web on smaller scales? Do their orbits trace hidden patterns that echo the grand design? To know this, we must turn our gaze to the satellites themselves, those faint companions often overlooked, yet essential to the story of the giant. Part 11. The Silent Companions. Every giant travels with an entourage, and Andromeda, the colossus next door, is no exception. Though its spiral arms dominate the sky, though its halo stretches nearly 1,000,000 light-years across, it is not alone. Around it circle dozens of smaller galaxies, faint companions bound by gravity, like moths orbiting a flame. They are easy to overlook, but their story is part of Andromeda's story. Without them, the giant would not be what it is. Look closer, and you will find them. M32, M110. Dozens more, each with their own shape and history, trailing quietly through Andromeda's halo. Some are bright enough to glimpse through amateur telescopes. Others are so faint they were only discovered in recent decades, revealed by deep surveys that mapped the night in exquisite detail. All of them are caught in Andromeda's pull. M32 is one of the strangest. It is a compact elliptical galaxy, small but dense, its stars packed together like grains of sand. Astronomers believe M32 was once larger, perhaps a spiral galaxy in its own right. But Andromeda's gravity stripped away its outer layers, tearing off its gas and most of its stars. What remains is a core, a remnant, a survivor, a fossil. M32 is not simply a companion. It is a witness to Andromeda's appetite. It bears the scars of its proximity to the giant. Then there is M110, larger than M32, but still a dwarf compared to Andromeda itself. It orbits at the edge of the halo, a faint elliptical glow. M110 contains traces of star formation, but its structure is irregular, disturbed, as though shaken by Andromeda's tides. Some astronomers suspect it, too, is being consumed. Slowly, silently, it is unraveling, its stars destined to become another faint stream in Andromeda's outskirts. And beyond these famous companions are many more. Over 30 dwarfs orbit Andromeda, most of them dim, diffuse, ghostly. Some are spheroidal, shapeless swarms of stars. Others are irregular, their gas stretched and twisted. Many are aligned in a thin plane, as though arranged on an invisible disk. Why? No one knows. The arrangement is too neat, too orderly, to be mere chance. Some wonder if it is the remnant of an ancient collision, a fossilized structure left from a great merger long ago. Others suggest it may point to new physics, a sign that our understanding of gravity is incomplete. Imagine the view from one of these satellites. If you stood on a planet orbiting a star in M32, Andromeda would not appear as a faint blur. It would fill the sky. Its spiral arms would stretch across the heavens, brighter than any moon. To live in such a place would be to live in the shadow of a giant, forever aware of the colossus, dominating the night. But for the satellites, that beauty is also doom. Over billions of years, their orbits decay. Andromeda's tides pull them apart. Already, streams of stars trace their unraveling. M32's outer layers are gone. Other dwarfs are little more than smears of stars, their shapes distorted, their gas stripped. The giant feeds on its companions, and the companions have no defense. This is the paradox of satellites. They are not only victims, they are also tools. Astronomers use them to weigh Andromeda, to measure the pull of its halo. The motions of M32, M110, and the dwarfs reveal the mass of the invisible dark matter cocoon. Without them, we would not know how large Andromeda truly is. In their surrender, they give us knowledge, and their chemistry tells another story. The stars of M32 are old, poor in metals. The stars of M110 are slightly richer. Each satellite carries its own chemical fingerprint, its own history of star formation. Together, they paint a picture of Andromeda's past. Some were born long ago and captured later. Others may be fragments of larger galaxies that were torn apart. Each is a piece of a puzzle we are still trying to assemble. What if these satellites are not merely companions, but survivors of Andromeda's cannibalism? What if they are the last remnants of galaxies that once rivaled it, reduced now to fragments orbiting their conqueror? If so, then M32, M110, and the others are ghosts, echoes of battles fought billions of years ago. But even ghosts have power, for their presence shapes Andromeda still. Their gravity tugs on its spiral arms. Their collisions stir its gas, igniting new stars. Their streams enrich its halo. the satellites are not passive. They are active participants in the galaxy's growth. Without them, Andromeda would not be the same. And here lies another mystery. The satellites of Andromeda are arranged in a thin, planar structure, stretching like a disk. The Milky Way's satellites, too, seem to form similar alignments. This defies our models of dark matter. According to theory, satellites should orbit in random directions, scattered like insects around a lamp. But instead, they seem ordered, organized, as if guided by something unseen. What force arranges them so neatly? Is it coincidence, or is it hint of a deeper law? Some scientists whisper that it may point to flaws in our understanding of gravity itself. That perhaps the satellites are not only companions, but messengers, telling us that our physics is incomplete. If so, then Andromeda's dwarfs may be more than faint smudges in the sky. They may be clues to the next revolution in science. Imagine it, dozens of tiny galaxies, invisible to the naked eye, holding within their orbits the secret to new physics. Imagine that the future of cosmology may depend not on the trillion stars of Andromeda, but on the handful of faint dwarfs circling it. What a paradox, what a wonder. Tonight, as you drift deeper into stillness, imagine yourself standing on the edge of one of those satellites. You look up, and there it is, Andromeda, stretching across the heavens, brighter than any full moon, filling the sky with rivers of stars. It is beautiful, it is terrifying, and it is inescapable. You are bound to it, as all satellites are bound to their giant. You are part of a story that ends in absorption, and this is our story too. For we, the Milky Way, are nothing more than a giant satellite ourselves, bound by gravity, destined for collision, already entwined in Andromeda's halo. We too are a companion of the Colossus. We too will one day be absorbed. So the satellites of Andromeda are not only a story of others, they are a mirror. They show us what we are and what we will become. They whisper our fate. But before that future arrives, there is something else to consider. For if satellites orbit giants, what orbits satellites? If the hierarchy extends downward, if even dwarfs have companions of their own, then the cosmos may be a nested system without end. To understand Andromeda fully, we must ask, what smaller structures orbit its dwarfs? What hidden systems lie within systems, like Russian dolls of starlight? That is where our journey turns next. Part 12. Nested Worlds. The universe loves to repeat itself. Patterns echo across scales, from the smallest atoms to the largest galaxies. And if Andromeda teaches us anything, it is that there is no such thing as isolation. Every system belongs to another. Every orbit is part of a larger orbit. The cosmos is a Russian doll of structure, nested without end. We know Andromeda as the giant spiral, a trillion stars wrapped in arms of light. But look closer, and you will see that even its faint companions have companions. Even its satellites have their own retinues. The hierarchy continues downward. Galaxies orbiting galaxies, clusters orbiting dwarfs, stars orbiting clusters, planets orbiting stars. The pattern does not stop. It unfolds endlessly, like a fractal written into space. Start with the globular clusters. Andromeda possesses more than 500 of them, dense spheres of stars orbiting far out in its halo. Each cluster contains hundreds of thousands of stars, crammed into volumes only a few dozen light years across. They are ancient, older than most of the stars in Andromeda's disk. Some date back over 12 billion years, relics from the dawn of galaxy formation. They are fossils, glowing orbs that preserve the conditions of the early universe. Imagine standing inside one. Stars would crowd the sky in every direction, dozens as bright as Venus, hundreds brighter than Sirius. Night would never be dark. It would be a constant ocean of starlight. To live in such a place would be to live in perpetual awe, surrounded by suns. And yet these clusters, dazzling though they are themselves tiny satellites of Andromeda, circling silently in its vast halo. Then there are the dwarf galaxies. We often think of them as simple, faint smudges. But they, too, can carry their own globular clusters, their own stellar systems. The hierarchy deepens. A dwarf galaxy orbits Andromeda. A cluster orbits the dwarf. Stars orbit the cluster. Planets orbit the stars. Moons orbit the planets. And so on, downward, endlessly repeating. What if some of these dwarfs harbor their own sub-satellites? Already hints of such systems have been seen around the Milky Way. The Sagittarius dwarf galaxy, which is being consumed by our own galaxy, once carried clusters of its own. Why not Andromeda's companions too? The pattern would hold. Every giant carries smaller companions, and those companions carry smaller still. A cosmic nesting that stretches as far as we can see, and farther. But this hierarchy is not only downward, it is upward too. Andromeda itself is part of the local group, which is part of the Virgo supercluster, which is part of the Laniakea supercluster, which may be part of something larger still. Each level contains the next. Each scale is part of another. If you step back far enough, the universe looks like a web of endless nesting, each structure both a whole and a fragment. Why does the universe love hierarchy? Perhaps it is simply gravity, creating structure on every scale. Perhaps it is deeper, a law of self-similarity, a cosmic fractal repeating patterns across space and time. The spirals of galaxies resemble the spirals of hurricanes. The filaments of the cosmic web resemble the filaments of neurons. The nesting of satellites resembles the nesting of molecules. Patterns recur, as if the universe itself is playing a single theme in infinite variations. For Andromeda, these nested worlds are not only decoration, they are clues. The motions of globular clusters reveal the shape of its halo. The orbits of satellites reveal its mass. Even the faintest subsystems trace the invisible structure of dark matter. To map the hierarchy is to map the giant itself. The small reveals the large. The companions reveal the colossus. And yet, there is mystery. Some of Andromeda's clusters are too massive, too luminous, to be ordinary globulars. Astronomers suspect they may be the stripped cores of dwarf galaxies, remnants of systems devoured long ago. If so, then even the clusters are ghosts, carrying within them the memory of galaxies that no longer exist. A cluster may be a fossil, or it may be a corpse. Either way, it is a story of hierarchy and destruction, of smaller worlds subsumed by larger. Imagine a globular cluster that was once the heart of a galaxy. Around it once orbited billions of stars, gas clouds, planets. Over billions of years, Andromeda tore away its outer layers, star by star, until only the dense nucleus remained. Today, it drifts in the halo as a faint ball of light. From a distance, it looks like a cluster, but in truth, it is the ghost of a galaxy, a skeleton hidden among the living. This is the nature of nesting, beauty built from loss, hierarchy built from conquest. The giant grows by absorbing the small, and the small survive only as fragments orbiting the giant. And yet, from this violence comes order. From this destruction comes structure. What if this nesting has no end? What if every globular cluster hides within it smaller structures we cannot yet see? What if within stars there are substars? Within atoms there are subatoms? Within space itself there are layers of deeper space? What if the pattern of nesting continues not only across scales of size, but across scales of reality itself? The thought is dizzying, but Andromeda invites it. For every time we look closer, we find more. Every time we step back, we see larger patterns. There is no bottom, there is no top. There is only the repetition of structure, endlessly unfolding. And here lies a more practical mystery. Many of Andromeda's globular clusters and dwarf satellites orbit in strange alignments, as though placed on a disk. Why? Did a single ancient collision scatter them into this pattern, or is there something deeper, an unseen law arranging them? If the hierarchy is so precise, could it be intentional? Could it be designed? We cannot know, but the question itself holds power, for it forces us to wonder whether the universe is simply chaotic, or whether its hierarchies hint at something more, a deeper order, a hidden architecture, a cosmic logic. Tonight, as you drift toward rest, imagine Andromeda not as a single galaxy, but as a kingdom of nested worlds. Imagine globular clusters orbiting like lanterns in the halo. Imagine dwarf galaxies circling silently, some with their own companions. Imagine stars crowding into dense clusters, planets circling stars, moons circling planets. Imagine the infinite pattern, up and down, in and out, larger and smaller, without end. And imagine that we are part of this hierarchy too. Earth is a satellite of the Sunday. The Sun is a satellite of the Milky Way. The Milky Way is a satellite of the local group, and the local group is a satellite of the cosmic web. We are satellites within satellites, endlessly nested. Andromeda's companions remind us of this truth. They are not just faint galaxies in the sky. They are mirrors. They show us that no system stands alone. They show us that we, too, are part of something larger, bound in orbits we cannot escape. And this brings us to the next question. If Andromeda is built of hierarchies, if its satellites are remnants of past collisions, then what does this say about its chemistry? What elements flow through its stars? What secrets lie in its light? To know Andromeda fully, we must not only map its structure, but taste its composition. That is where our journey turns next. Part 13. The chemistry of giants. Every star has a voice. Every star sings in light. And when we listen closely, when we split that light into its hidden colors, we hear more than brightness. We hear chemistry. Andromeda, the colossus next door, glows with 1 trillion voices. Its stars span every stage of life, from blue giants burning fast to red dwarfs glowing steadily for trillions of years. Its gas clouds shimmer with the birth of new suns. Its core is filled with the faint red light of ancient stars, long past their youth. Each of these voices carries a chemical story, and together they reveal the biography of a galaxy. When astronomers study Andromeda, they do not merely look at it. They listen to its spectrum. Starlight, when spread into a rainbow, is crossed with thin, dark lines. These are absorption lines, the fingerprints of elements: hydrogen, helium, oxygen, carbon, iron, calcium. Every element leaves its mark, a subtle absence where light has been absorbed by atoms. By reading those marks, scientists know what Andromeda is made of, and what a story those marks tell. Andromeda's stars are rich in heavy elements, what astronomers call metals. These metals are not forged in the Big Bang. They are the ashes of stars. Every carbon atom in Andromeda was created in the heart of a red giant. Every atom of oxygen was born in the furnace of a massive star and scattered in a supernova. Every atom of iron was forged in the collapse of stellar cores. To study Andromeda's chemistry is to study its history of death and rebirth. Some of Andromeda's stars are old, poor in metals. These belong to the galaxy's halo, relics of its youth, born before many cycles of starbirth had enriched the gas. Others, especially those in the spiral arms, are younger, richer in carbon, oxygen, and iron. These stars are the children of countless supernovae. Their chemistry is evidence of the galaxy's cannibalism. Too, for the stars of devoured galaxies carried their own fingerprints, now mixed into Andromeda's bloodstream. Imagine it. A dwarf galaxy falls into Andromeda, torn apart by tides. Its stars scatter, but its gas is stripped and ignites new star formation. Those new stars, though born in Andromeda, carry the chemistry of the smaller galaxy. Every absorption line in their spectra is a whisper of another system, a memory preserved in light. This is why astronomers say galaxies are not static objects, but ecosystems. They breathe, they recycle, they live. Andromeda has been breathing for more than 10 billion years, inhaling gas, exhaling stars, enriching its chemistry with each generation. Its metallicity, the abundance of heavy elements, has risen steadily over time. The spiral arms we see glowing tonight are not the same as they were billions of years ago. They are richer, heavier, more complex. And this chemistry matters for life. Life as we know it requires carbon, nitrogen, oxygen, iron, phosphorus. These elements are forged only in stars. Without them, there would be no DNA, no oceans, no blood. In Andromeda, as in the Milky Way, life's elements are abundant. The galaxy is fertile. Somewhere among its trillion stars, planets orbit quietly. And on some of those planets, perhaps chemistry has crossed into biology. Perhaps the cycle of starlight has already given rise to minds looking back at us. What if, right now, a civilization in Andromeda is studying the Milky Way's spectrum? What if they see our fingerprints, our chemistry, our richness in heavy elements, and wonder, do they harbor life? Do they look back at us as we look at them? The thought is dizzying. Across 2.5 million light years, two galaxies might be reading each other's light, silently asking the same question. Andromeda's chemistry is not uniform. Its core is older, redder, poorer in metals. Its arms are bluer, younger, richer. Its halo is a museum of ancient stars, metal poor and dim. Its globular clusters are fossils, some with chemistry distinct from the main galaxy, evidence of their foreign birth. Each region of Andromeda carries a different story, a different fingerprint, a different chapter in the Book of Starlight. But there is mystery here, too. Some stars in Andromeda's halo are surprisingly metal-rich, more than expected for their age. Did they come from devoured galaxies? Or does Andromeda's past contain episodes of furious star formation, bursts so intense they enriched the gas more quickly than in the Milky Way? The puzzle remains unsolved. The chemistry does not always add up. And what about Andromeda's gas clouds? The great nebulae scattered through its arms are laboratories of chemistry, glowing with emission lines of hydrogen and oxygen, laced with dust grains of carbon and silicon. These clouds are where new stars are born, where the chemistry of life is forged anew. Their light, when spread into a spectrum, is not just a fingerprint of elements, it is a promise of futures. Stars yet to form, planets yet to shine, civilizations yet to awaken. We can even measure the motion of gas through its chemistry. Emission lines shift depending on velocity. Some clouds stream inward, falling toward Andromeda's core. Others stretch outward, flung by past collisions. Each one tells a story of motion, of flow, of change. The galaxy is alive, its chemistry in constant flux, and then there are the mysteries hidden in the ultraviolet, the infrared. With Hubble, with Gaia, with the James Webb Space Telescope, astronomers have probed deeper, measuring faint signatures invisible to the human eye. They find unusual ratios, hints of processes not fully understood. The chemistry of giants is not simple. It is layered, complex, enigmatic. What if Andromeda's chemistry is not only history, but message? What if its unusual stars, its strange ratios, are not accidents, but signs of something more? Some have dared to speculate. Could advanced civilizations leave chemical signatures in their stars? Could they enrich certain elements deliberately, marking their presence across the galaxy? If so, perhaps Andromeda already bears such marks, waiting for us to decode them. We cannot know, but the idea lingers. The chemistry of starlight may hold more than we realize. It may be a language, and if so, then Andromeda's trillion voices may be speaking even now. Tonight, as you close your eyes, imagine Andromeda not just as light, but as language. Every star a word, every spectrum a sentence, every absorption line a story. Imagine the galaxy as a book written in fire, its pages spanning 220,000 light-years, its chapters stretching across billions of years. Imagine reading it, one line at a time, across the void. And imagine that somewhere, someone in Andromeda is reading us too. This is the beauty of chemistry. It turns light into meaning. It turns distance into story. It turns silence into conversation. And in that conversation, Andromeda reveals itself not just as a colossus, not just as a predator, but as a storyteller of its own. But there is another layer we have not yet touched. Chemistry tells us what Andromeda is made of, but motion tells us where it is going. If we want to understand its full destiny, we must study its velocity, its trajectory, its speed through the void. We must ask, how fast is the Colossus moving? How quickly is it approaching us? What does its motion mean for our future? That is where our journey leads next. Part 14. The Speed of Destiny. Look up on a clear night, and Andromeda seems still. A faint blur, barely visible, suspended in silence. It does not move to the naked eye. It does not drift from its place among the constellations. But this stillness is an illusion. Andromeda is not fixed. It is racing toward us. It is moving with a speed so great that the numbers seem absurd. Astronomers have measured it carefully. Using the Doppler effect, the shift in light caused by motion, they find that Andromeda is approaching at nearly 70 miles per second. That is more than 250,000 miles per hour. In the time it takes you to listen to this chapter, Andromeda will have moved tens of thousands of miles closer. Silent, invisible, inevitable. Pause on that thought. A galaxy of 1 trillion stars, each blazing with its own light, is moving toward us at a speed faster than any spacecraft humanity has ever built, and yet we do not feel it. We live our lives in quiet, while the Colossus closes the gap. How do we know this? The answer lies in light. When a source of light moves toward us, its waves are compressed, shifted toward the blue. When it moves away, they are stretched, shifted toward the red. Andromeda's spectrum is blue shifted. This is rare. Almost every other galaxy in the universe is red shifted, carried away from us by the expansion of space. But Andromeda is the exception. It is coming closer. It is one of the few galaxies defying the push of dark energy, its gravity pulling it inward against the tide. This blue shift is not just a number, it is a prophecy. It tells us that in about 4 billion years, the Milky Way and Andromeda will meet. In about 5 billion years, they will merge. Our skies will change forever, and yet, there is more subtlety here. For decades, astronomers wondered, is Andromeda heading straight for us, or will it pass by, grazing the edge of our galaxy? To answer this, they needed more than the radial velocity, the speed toward us. They needed the tangential velocity, the sideways motion across the sky. Measuring such tiny shifts is extraordinarily difficult. It requires precision so fine it borders on the impossible. But with the Hubble Space Telescope, scientists succeeded. They tracked Andromeda's stars across the sky, measuring their drift against distant quasars. The result? Andromeda's sideways motion is small, very small, too small to miss us. The conclusion is clear. The collision is not a possibility, it is destiny. But destiny is not simple. The galaxies will not collide in a single crash. Instead, they will pass through each other, drawn back by gravity, colliding again and again, in a slow dance lasting billions of years. Each pass will distort them, stretching their arms, flinging stars into long tails. Some stars will be ejected entirely, hurled into intergalactic space. Others will fall inward, feeding the black holes at the cores. After several encounters, the two spirals will settle into one massive elliptical galaxy, Milkomeda. Imagine the sky as this unfolds. In a billion years, Andromeda will appear larger than the moon, its spiral arms filling the heavens. In 2 billion, the arms of both galaxies will intertwine, streams of stars arcing from horizon to horizon. In 4 billion, the cores will glow together, brighter than any star, dominating the night. The constellations we know will vanish, the sky will be rewritten, and through it all, the solar system will drift. We may survive untouched, carried into a new orbit within Milkomeda, or we may be flung outward, exiled to the galaxy's edge. Our fate is uncertain. But the larger fate is not. Andromeda and the Milky Way will merge. What if we could ride alongside? What if we could watch the galaxies close the distance, not over billions of years, but in accelerated vision? We would see Andromeda swell, its arms unfurling, its core brightening. We would see the two spirals stretch into long, distorted shapes, stars scattered like sparks from a fire. We would see them embrace, recoil, embrace again. And finally, we would see them fuse into one glowing orb. It would be chaos, it would be beauty, it would be destiny written in light. But even as we imagine, there is unease. For motion is never simple. Andromeda's approach is not perfectly straight. Its halo interacts with ours already, its streams overlapping, its dark matter blending with our own. The merger is not a future event. It has begun, slowly, invisibly. Every moment, the halos entwine more deeply. Every moment, the galaxies grow more bound. What if this binding is already altering us? What if the Milky Way's spiral arms, its satellite galaxies, its very structure, are being tugged by Andromeda even now? Some astronomers believe the warping of our outer disk, the strange tilts of our satellites, may be signs of Andromeda's pull. If so, the dance has already started. The first steps are already taken. We are participants in a ballet too vast to see. And here is another question. What if Andromeda's velocity is not constant? What if interactions with other galaxies, with the local group itself, are changing its path? Could its approach be faster than we think? Could the collision come sooner? Most models say no. But the universe is not always predictable. Surprises may lurk in the numbers. For now, the prophecy stands. 4 billion years. A number too vast to touch, and yet strangely intimate. For in 4 billion years, our sun will be near the end of its life, swelling into a red giant. Earth, if it still exists, will be uninhabitable. Humanity may be gone, or it may be among the stars. The merger of galaxies and the death of the sun may coincide, two cosmic endings unfolding at once. What poetry lies in that symmetry? But perhaps, just perhaps, it is not an ending. For while the Milky Way will vanish, and Andromeda will vanish, what emerges will be greater. Milkomeda will be vast, luminous, rich in stars. It will shine for trillions of years, long after smaller galaxies fade. It will be a beacon in the darkening universe, a last island of light in a sea ruled by dark energy. In a sense, the collision is not destruction, it is transformation. Tonight, as you rest beneath the quiet sky, imagine the motion you cannot see. Imagine Andromeda racing toward us at 250,000 miles per hour, silent, steady, unstoppable. Imagine the sky of the future, filled with its arms, its stars, its core. Imagine the destiny of two galaxies, entwined by gravity, their paths written into the fabric of space. And then, let yourself wonder, what greater motions are we missing? If galaxies collide, what about clusters? If clusters collide, what about superclusters? The universe is not still. Nothing is at rest. Everything is moving, drawn together or pushed apart, guided by forces we barely understand. Andromeda's motion is not only its story, it is a glimpse of the universal truth. All things are in motion. All things are in flux. All things are part of a dance without end. And this leads us into the next mystery. For speed tells us where we are going, but mass tells us how. To understand Andromeda's full power, we must weigh it. We must ask, how heavy is the Colossus? How does its mass compare to the Milky Way? What secrets are hidden in its trillion suns? That is the next chapter of our journey. Part 15. Weighing the Colossus. How heavy is a galaxy? It seems like an impossible question. A galaxy is not a single object, not a stone you can place on a scale. It is a trillion stars, clouds of gas, dark matter halos, streams of satellites, all bound together by gravity. And yet, astronomers have tried to weigh Andromeda. They have tried to answer the unanswerable. The results are staggering. To begin, consider the visible matter. A trillion stars. If each one were a sun, the total mass would already be overwhelming, about 1 trillion times the mass of our Sunday. But not every star is the same. Some are red dwarfs, smaller and dimmer. Others are blue giants, heavier and brighter. Adding them together, with all their diversity, gives us a first estimate. Several 100 billion solar masses in stars alone. Then comes the gas, hydrogen, and helium spread through the spiral arms, glowing in nebulae, collapsing into new suns. Gas adds another few 100 billion. Already, Andromeda is a monster. And yet, this is only the surface. For when astronomers measure the orbits of Andromeda's stars, they find something strange. The outer stars move too fast. They orbit the galaxy at nearly the same speed as those near the center, defying Newton's expectations. This is the fingerprint of dark matter. An invisible mass outweighs the visible one. It is the hidden bulk of Andromeda, the reason its stars do not fly apart into space. How much dark matter? Enough to multiply the total by a factor of 5 to 10, which means Andromeda's total mass is not just 1 trillion suns, but closer to 1.5 trillion to 2 trillion solar masses. Twice as heavy as the Milky Way, perhaps more. If the Milky Way is a giant, Andromeda is a colossus. It is the heavyweight champion of the local group. But how do we measure such enormity? Astronomers use the motions of satellites M32, M110, and the smaller dwarfs that orbit the giant. Their speeds reveal the gravity pulling them. The faster they orbit, the heavier Andromeda must be. It is the same method Newton used to weigh Earth by studying the moon, applied on a galactic scale. But even this is not enough. Satellites can be deceptive. Some are falling in for the first time, not bound in long-term orbits. Others have been disturbed by collisions. Their motions carry uncertainty. So astronomers turn to globular clusters, those ancient balls of stars orbiting in the halo. Their orbits are less chaotic, their paths longer, steadier. By mapping hundreds of clusters, scientists trace the pull of the invisible halo. The result always points to the same truth. Andromeda is heavier than we once thought. Another clue lies in gravitational lensing. Light from distant quasars bends as it passes through Andromeda's halo. The amount of bending depends on mass. By measuring these subtle distortions, astronomers weigh the dark matter cocoon itself. Again, the numbers climb. Again, the colossus grows. And yet, there is uncertainty. Some studies suggest Andromeda may not be much heavier than the Milky Way. Others say it may be twice as heavy. The truth may lie in between. The problem is that galaxies are not solid objects. Their halos fade into the void, with no sharp boundary. Where do you stop measuring? At the edge of the visible disk? At the faintest star? At the limit of the halo? The answer changes the number. The galaxy resists being weighed, as if it wants to keep its true size secret. But whatever the exact figure, one truth is clear. Andromeda outweighs us. Its mass gives it dominance. Its gravity shapes the local group, binding dozens of smaller galaxies. The Milky Way and Andromeda are the two rulers, but Andromeda is the senior partner. It is the mountain beside our hill, the giant beside our giant. What does this mean for the future? It means that when the collision comes, Andromeda's mass will give it the upper hand. The Milky Way will be pulled, stretched, distorted more than its partner. Our galaxy will unravel first, its stars scattered into streams, while Andromeda's core holds steady. In the final merger, the Colossus may absorb us more than we absorb it. The new galaxy will carry Andromeda's weight, Andromeda's black hole, Andromeda's dominance. The Milky Way will vanish into the larger name. But there is poetry in this too. For though we will be consumed, we will also become part of something greater. The mass of Andromeda and the Milky Way together will create a galaxy of 3 trillion solar masses, a colossus to outshine most in the local universe. It will be an empire of stars, luminous and immense. Our sun, if it survives, will orbit within that new system, a tiny spark in a vast kingdom. We will not disappear, we will be transformed. And here lies the paradox. To weigh Andromeda is to weigh destiny itself. Its mass determines the speed of collision, the violence of the merger, the fate of our stars. Its gravity is not just a number, it is a prophecy. Every solar mass adds weight to the story of our future. Every hidden particle of dark matter is a silent force shaping what will come. What if Andromeda is even heavier than we think? What if its halo extends farther? Its satellites are more bound, its streams more massive. Then the collision may come sooner, the merger more violent. What if, instead, it is lighter? Then perhaps the Milky Way will play a greater role, shaping the outcome more than expected. The balance is delicate, the future uncertain, and yet, the merger itself remains inevitable. The dice may be loaded, but they will still fall. Tonight, imagine the weight of Andromeda pressing down on the fabric of space. Imagine a trillion stars, a trillion suns, all bound in a single system. Imagine the invisible halo stretching farther than sight, heavy beyond comprehension. Imagine the gravity that binds not only its own stars, but its satellites, its clusters, even us. For we, too, are already caught in its pull. Our Milky Way and Andromeda are not separate. They are parts of one system, already entwined, already fated to merge. And so the act of weighing is not only science, it is intimacy. It is the recognition that our future is bound to a mass beyond comprehension, a colossus whose weight shapes our destiny. To weigh Andromeda is to weigh ourselves, but weight is only one measure. To know Andromeda fully, we must also know its light. How bright is it? How luminous are its stars? How does its glow compare to the Milky Way's? Light, after all, is how we see it, how we connect with it across 2.5 million light years. The next step in our journey is to measure not its weight, but its radiance. Part 16. The radiance of a trillion suns' light is the language of the universe. It is the messenger that crosses the void, the signal that survives when everything else is silence. And Andromeda, the colossus next door, speaks in light more powerfully than almost any other galaxy in the sky. To the naked eye, it looks faint, a blur, a smudge. Many who pass beneath the stars never see it at all. And yet appearances deceive. That faint blur is the combined glow of 1 trillion stars. If your eyes were sensitive enough, Andromeda would not look small. It would stretch 6 times the width of the full moon across the heavens. Its glow would dominate the night. We are blinded not by its absence, but by our own limits. Astronomers measure luminosity, the intrinsic brightness of a galaxy, by summing the light of its stars. For Andromeda, the number is astonishing. About 25 billion times the brightness of the Sunday. Imagine that for a moment. A single star, multiplied a trillion-fold, woven together into a glow that has been traveling across space for 2.5 million years before it reaches us. The light you see tonight left Andromeda long before the first humans walked Earth. Each photon is an ancient traveler carrying history across the void. But this light is not uniform. Its core glows with the reddish tones of old stars' giants at the end of their lives. Long-lived dwarfs burning steadily. Its spiral arms shine blue with young stars, hot and massive, blazing brightly but briefly. The arms are also dotted with nebulae, clouds of glowing gas where new stars ignite. The contrast is striking. The calm red of age beside the fierce blue of youth, the the quiet core beside the blazing arms. Andromeda is not a single age, it is a city of light, old and new coexisting. What if we could see Andromeda not in white light, but across the spectrum? In ultraviolet, its youngest stars blaze like torches, outlining its spiral arms. In infrared, its dust lanes glow faintly, revealing rivers of material that fuel star formation. In X-rays, remnants of supernovae flicker, evidence of past violence. Each wavelength tells a different story, and together, they paint a portrait of a galaxy alive with complexity. Yet for all its radiance, Andromeda is not the brightest galaxy we know. There are quasars far more luminous, galaxies ablaze with furious starbursts. But Andromeda's beauty lies not in extreme outbursts, but in balance. It glows steadily, a trillion stars woven into a harmony of light. It is not a shout, it is a choir, and this glow has power. Light from Andromeda was the first to reveal to humanity that the Milky Way is not alone. When Edwin Hubble measured the Cepheid variables within its glow, he proved that Andromeda lay outside our galaxy. Its light was the messenger that expanded the universe. Without it, we might still think the Milky Way was the whole of existence. Andromeda's radiance was our awakening, but there is strangeness in its glow too. Some regions of Andromeda are dimmer than expected, as if dust clouds hide more than they reveal. Some streams of stars in the halo shine faintly, relics of devoured galaxies. Even its globular clusters emit unusual signatures, too bright or too dim for their age. Light does not only reveal, it also conceals, and in Andromeda, the balance of radiance and shadow is delicate, layered with mystery. What if Andromeda's light is not only natural? What if civilizations exist within it, adding their own glow to the stars? It is a question astronomers dare to ask. Could advanced species build structures so vast they alter a galaxy's luminosity? A Dyson swarm around a star, a megastructure intercepting starlight, could dim its spectrum. On a galactic scale, such engineering might leave fingerprints. Have we already seen such fingerprints in Andromeda's glow and not recognized them? Could part of its light be artificial? We cannot know. But the thought lingers. When we look at Andromeda, we may be seeing not just nature, but history, and perhaps even intelligence. And yet, light is fragile. It fades with distance, scattered by dust, absorbed by gas. The photons that reach us have traveled for millions of years, dodging obstacles, surviving the emptiness. Most are lost. Only a fraction arrive. What we see is a whisper compared to the roar. If we were closer, if Earth orbited a star on the edge of Andromeda, the sky would blaze. The galaxy would cover half the heavens, a radiant ocean of light. Our nights would never be dark. Our myths would be different, our sense of scale transformed. Even from here, Andromeda changes our perspective. It reminds us that faintness is not absence. What looks like a blur is in truth an empire of stars. What looks like stillness is in truth motion. What looks like a neighbor is in truth a giant. The radiance of Andromeda also reminds us of time. Every photon is old. The light you see tonight left the galaxy when early humans were still shaping stone tools. When the light began its journey, the Ice Age had not yet come, the pyramids had not yet risen, Rome had not yet fallen. Entire civilizations have risen and fallen while those photons traveled across space. And yet they arrived tonight, steady, unbroken, faithful. What if light itself is memory? What if the glow of Andromeda is a record, a history written not in words but in photons? If so, then every night sky is a library, and Andromeda is one of its grandest books. We have only begun to read its pages. Astronomers measure its brightness, map its colors, trace its spectra, but beyond the numbers lies the poetry. A trillion stars, shining together, speaking across time. The radiance of a giant, reaching across the void to remind us that we are not alone. And this brings us to a deeper question. What fuels this radiance? What processes ignite these stars, sustain them, recycle their ashes into new generations? To understand Andromeda's light fully, we must descend into the engines of starlight. We must enter the nuclear furnaces of its stars, the alchemy that turns hydrogen into fire. That is where our journey will go next. Part 17, The Engines of Fire. Every star is a miracle, a sphere of gas that should collapse under its own weight, yet somehow resists. How? By fire, not fire as we know it, but fusion, the alchemy of the cosmos. And in Andromeda, with its trillion stars, that miracle repeats a trillion times. If you could drift inside one of Andromeda's blazing arms, you would see countless furnaces at work. Blue giants burning fast, red dwarfs glowing slowly, white-hot clusters of newborn suns. Each one is a self-sustaining engine, balancing gravity's pull with the push of nuclear reactions. Together, they light the galaxy, pouring radiance into space for millions and billions of years. But the process is simple, in its essence. Hydrogen, the most abundant element in the universe, is fused into helium at the star's core. In that transformation, a tiny fraction of mass is lost, converted into pure energy by Einstein's equation, E equals mc squared. That equation is the true heartbeat of the cosmos. Every photon that ever touched your skin, every beam of sunlight that warmed Earth, every flicker from Andromeda's stars, all of it is mass turned into light. The blue stars in Andromeda are the most ferocious, dozens of times more massive than our sun. They burn their fuel quickly, living for only a few million years. They shine brilliantly, their spectra laced with helium and heavier elements, their cores racing through fusion cycles that create oxygen, carbon, and neon. But their brilliance is brief. They die young, exploding as supernovae, scattering new elements into the galaxy. Their deaths seed the next generation of stars, the next round of planets, the next chance for life. The red dwarfs are the opposite, small, cool, dim. They burn hydrogen so slowly that they can live for trillions of years. Most of Andromeda's stars are red dwarfs, faint but eternal, quietly sustaining themselves while their brighter cousins live fast and die young. If life exists in Andromeda, perhaps it thrives around such stars, stable for timescales longer than the age of the universe itself. And then there are the middleweights, stars like our Sunday, steady, balanced, long-lived. They burn hydrogen for billions of years, shining with quiet persistence. Many such stars exist in Andromeda, scattered through its spiral arms, circled by planets we cannot yet see. Each one is a potential harbor for life. Each one is a fire that may warm oceans, forests, or skies we can only imagine. But fusion does not end with hydrogen. In the most massive stars, when hydrogen is exhausted, helium begins to fuse into carbon and oxygen. Later still, carbon into neon, neon into magnesium, oxygen into silicon, silicon into iron. Each step yields new elements. Each step builds the periodic table. But when iron forms, the chain ends. Fusion of iron consumes energy instead of releasing it. At that point, the balance fails. Gravity wins. The star collapses, detonates, and dies. What remains is either a neutron star, dense as a city made of atomic nuclei, or a black hole, an abyss of gravity. These remnants join Andromeda's vast population of dark companions. The cycle is complete. Stars born, stars living, stars dying, stars seeding the next. Andromeda is not static in its fire. Its rate of star formation has changed across time. Billions of years ago, during its great mergers, collisions of gas clouds ignited furious bursts of star birth. The galaxy blazed with new light. Today, its pace is calmer. It still births new stars, but fewer, slower. The fire still burns, but less fiercely. One day, billions of years from now, it may exhaust its gas, its arms growing dim, its glow fading. But for now, it is still alive, still fiery, still radiant. The engines of fire are not just sources of light, they are forges of destiny. Every atom of carbon in your body, every atom of oxygen you breathe, was created in a star. The iron in your blood was born in a supernova. You are made of Andromeda's process, even though you live in the Milky Way. The same physics that lights its trillion stars lit our sun and forged you. What if Andromeda's stars host their own Earths? What if chemistry has blossomed into biology on countless worlds, warmed by the fire of alien suns? Somewhere in Andromeda, beneath skies we will never see, minds may be asking the same questions we ask tonight. Minds made possible by fusion, by fire, by the transformation of hydrogen into light. What poetry, that we might both exist two civilizations separated by 2.5 million years of light travel, both gazing outward, both wondering if they are alone. But there is a darker side to fire, for stars are not eternal. The blue giants burn themselves out. The yellow suns swell into red giants, shedding their outer layers into glowing nebulae, leaving behind white dwarfs that slowly cool into black cinders. Even the red dwarfs, long-lived though they are, will one day exhaust their fuel. The engines will stop, the galaxy will grow dim, the universe itself will cool. And yet, the fire does not truly end, for the ashes of stars become the seeds of new stars. The nebulae enrich the galaxy with fresh elements, enabling more complex chemistry. The cycle repeats. Andromeda is not simply burning itself away. It is renewing itself, generation after generation. Its fire is not only destruction, it is creation. Astronomers studying Andromeda's starlight see patterns in its chemistry that tell of these cycles. Stars in its halo are old and metal-poor, born before many supernovae enriched the gas. Stars in its arms are younger and metal-rich, evidence of countless generations before them. Each spectrum is a record of fire. Each photon is a trace of fusion. The galaxy is a layered history of burning. But what if fusion is not the only story? What if other processes, unknown to us, occur in Andromeda's stars? We assume the same laws apply everywhere. We assume hydrogen fuses into helium there as it does here. But what if subtle differences exist? What if Andromeda's most massive stars produce unusual ratios of elements? Or if exotic particles alter their evolution? Could Andromeda hold surprises in its fire? Could it conceal physics we have not yet discovered? Perhaps. The more we study, the stranger things become. Some of Andromeda's globular clusters show unexpected chemical signatures, stars with anomalous abundances of helium or sodium. Why? Are they the products of unusual fusion processes, or the remnants of galaxies consumed long ago? We do not yet know. The fire still holds secrets. Tonight, as you let your mind drift, imagine Andromeda not as a blur, but as a trillion suns, each one an engine of fire. Imagine the blue giants, short-lived and blazing, consuming themselves in brilliance. Imagine the red dwarfs, steady and quiet, burning slowly through eternity. Imagine the countless middleweights, stars like our sun, glowing patiently for billions of years. Imagine the cycle of birth and death, the forging of elements, the scattering of ashes, the rise of new generations. Imagine, too, that somewhere among them, planets circle quietly, some rocky, some gaseous, some barren, some perhaps alive. On those worlds, perhaps creatures gaze at their own night skies and see the Milky Way as a faint blur. Perhaps they wonder what fuels its glow. Perhaps they, too, dream of the engines of fire. This is Andromeda's secret. It is not just a galaxy, it is a furnace, a trillion furnaces burning, forging, renewing. Its light is not just brightness. It is the sum of countless transformations, the sum of countless lives and deaths. To understand Andromeda is to understand fire itself. And yet, this is not the end of the story. For fire does not exist alone. Fire shapes time. Stars live and die on cosmic timescales, and their rhythms define the history of galaxies. To understand Andromeda fully, we must ask, how old is it? How do its stars mark its age? What is the chronology of the Colossus? That is where our journey will go next. Part 18, The Age of Giants. Every life has a timeline. Every being has a birth, a growth, a maturity, and an end. Galaxies, though vaster than imagination, are no different. Andromeda, the most colossal spiral in our skies, carries within its stars the history of more than 10 billion years. To know its age is to read the biography of a giant. But how do you measure the age of something so vast? You cannot cut it open like a tree and count the rings. You cannot ask it directly. Instead, you must listen to its stars. For stars are clocks. They carry in their light the memory of when they were born. By studying their colors, their compositions, their motions, astronomers reconstruct the timeline of Andromeda's life. The first chapter began over 10 billion years ago. The universe was young then, only a fraction of its current age. Clouds of hydrogen and helium swirled together, collapsing into the first proto-galaxies. In that era, Andromeda was not yet the spiral we know. It was a collection of small fragments, star-forming clumps drawn together by gravity. These clumps merged, colliding violently, igniting bursts of starbirth. Some of the stars created in that era still shine today, dim and red in Andromeda's halo. They are the elders, the fossils, the witnesses to the galaxy's youth. The second chapter came when Andromeda grew larger, around 8 to 9 billion years ago. Evidence suggests it underwent a major merger not with a dwarf, but with another galaxy nearly its size. The scars remain in the motions of its stars, in the strange alignments of its satellites, in the streams that curve across its halo. This ancient collision may have defined Andromeda's future, swelling its mass, building its bulge, igniting furious starbursts. For millions of years, its core may have blazed like a quasar, a beacon across the universe. Then, as the chaos settled, a new galaxy emerged, larger, heavier, and destined to become the giant we see today. The third chapter unfolded more gently, across billions of years. Andromeda continued to grow, absorbing dwarfs, stripping gas from companions, enriching its chemistry. Its spiral arms stretched wider, its disk thickened, its satellites multiplied. During this time, the Milky Way too was growing, following a parallel path. Two giants, evolving side by side, bound invisibly, their fates already intertwined. We know this middle era by studying Andromeda's globular clusters. Some are ancient, more than 12 billion years old, relics of the dawn. Others are younger, only a few billion years old, evidence of later mergers. The variety of ages shows that Andromeda did not form in a single burst. It grew over time, layer by layer, each generation of stars adding to the story. And now, we are in the fourth chapter, the present. Andromeda is mature, massive, luminous. Its star formation rate has slowed compared to its youth, but it still creates new suns in its arms. It still absorbs dwarfs. It still grows, though more quietly. It is a galaxy at the height of its power, a giant in full bloom, but even as it thrives, we see hints of what is to come. In about 4 billion years, the next chapter will begin, the collision with the Milky Way. This future is not guesswork. It is written into its velocity, its trajectory, its gravity. The two galaxies are already bound, already entwined. Their halos overlap, their fates sealed. The collision is not a distant possibility. It is the next step in the story. And beyond that, farther still, the final chapters await. After the merger, after the birth of Milkomeda, star formation will eventually slow. Gas will be consumed, or ejected, or heated beyond use. The galaxy will fade into quiescence, glowing only with the light of aging stars. Over trillions of years, even those stars will dim. White dwarfs will cool, red dwarfs will fade, black holes will dominate, the engines of fire will fall silent, the giant will die. This is the fate of all galaxies. Andromeda is no exception. But perhaps that is too bleak, for even in death, galaxies leave legacy. Their stars, scattered across space, will continue to shine long after the spiral arms have dissolved. Their elements, forged in countless furnaces, will remain, shaping new worlds. The atoms in your body will endure, long after galaxies fade. The story of Andromeda is not only a story of beginnings and endings, it is a story of transformation, of continuity across scales of time beyond comprehension. Astronomers piece together this story with patience. They measure the spectra of stars in the halo, reading the fingerprints of age. They map the streams of cannibalized galaxies, tracing ancient collisions. They simulate Andromeda's growth in supercomputers, watching virtual galaxies merge and evolve. Each method adds detail to the timeline. And though uncertainties remain, the broad strokes are clear. Andromeda is about 10 billion years old, perhaps slightly older, perhaps slightly younger, old enough to be ancient, young enough to still blaze with life. And this age carries meaning, for it means that Andromeda and the Milky Way are nearly the same age. We are twins, born from the same cosmic era, shaped by the same forces. Our destinies are linked not only by gravity, but by history. We have grown up together in the same neighborhood of the universe, and we will grow old together, merging into one. What if galaxies have memories? What if every star, every orbit, every chemical fingerprint is a page in a book too vast for us to read in full? Then Andromeda's age is not only a number, it is a biography. It is the record of everything it has endured, every collision, every starburst, every quiet age of growth. Imagine it. 10 billion years ago, Andromeda was a cluster of faint lights, small clumps of stars forming in the dark. 5 billion years ago, it was a turbulent giant, blazing with starbirth, devouring neighbors. Today, It is a serene spiral, glowing steadily, a colossus beside us. Tomorrow, it will be something else larger, merged, transformed. The story is long, but every moment belongs to the same whole. And here lies the lesson. Age does not diminish a galaxy, it enriches it. Andromeda is not beautiful despite its history. It is beautiful because of it. Its scars, its streams, its diversity of stars all are evidence of a long life well lived. Without its age, it would not be what it is. Without its history, it would not shine so brightly. Tonight, as you drift deeper into stillness, imagine the timeline of Andromeda stretching before you. From the first stars igniting in darkness, to the great mergers that swelled its mass, to the quiet present, to the inevitable collision with the Milky Way, to the distant death of starlight. Imagine holding that story in your mind, not as a line, but as a cycle fire, collapse, rebirth, silence. Imagine knowing that you are part of the same cycle. Your atoms were forged in stars. Your future lies in the same destiny. You and Andromeda share the same history of fire, and yet, the timeline of a galaxy is not only about age, it is also about rhythm. Galaxies have pulses, bursts of star formation, lulls of quiet, cycles of violence and calm. If we want to understand Andromeda fully, we must trace not only its age, but its rhythms. We must listen to the heartbeat of the giant. That is where our journey turns next. Part 19. The heartbeat of a galaxy. A galaxy is not silent. It does not simply exist as a static swirl of stars. It breathes. It pulses. It has rhythms that span billions of years longer than the lives of suns, longer than the lifetimes of worlds. If you could compress time, if you could watch Andromeda unfold over eons the way you watch waves on the sea, you would see it beat like a living heart. The first pulse is star formation. Galaxies do not create stars at a constant rate. They flare with bursts, then grow quiet, then flare again. Andromeda is no exception. In its youth, when it was swollen with gas, it burned with furious creation. Millions of stars were born every year. Its spiral arms blazed blue with young suns. Its nebulae erupted with new light. Then came quieter periods, when the fuel thinned, when the fires dimmed. Later still, mergers triggered fresh bursts, reviving the giant with new generations. Astronomers see these rhythms in the age distribution of stars. Some are ancient, more than 10 billion years old, relics of Andromeda's first heartbeat. Others are intermediate, born during the great merger that may have occurred 8 billion years ago. Still others are young, created only a few 100 million years ago, evidence that Andromeda still breathes, still pulses, still beats. Another rhythm comes from its spiral arms. They are not fixed structures, frozen in place. They are waves, density waves, moving through the disk, compressing gas, triggering starbirth as they go. Like ripples circling outward on a pond, they pass through, over and over, setting the rhythm of light across the galaxy. A spiral arm is not a trail of stars. It is a traveling wave, and Andromeda's arms are its heartbeat, pulsing through the disk every few 100 million years. Even the black hole at its core contributes to this rhythm. In the distant past, it likely flared, igniting as gas fell inward. For a time, Andromeda may have pulsed as a quasar, blazing brighter than all its stars combined. That heartbeat has quieted, but it could return. If a fresh cloud of gas falls inward, the giant's core will awaken again, thundering with X-rays and jets of radiation. Quiet now, but not forever. The heart may beat again, and then there are the cycles of cannibalism. Every few billion years, Andromeda absorbs a dwarf galaxy. Each collision is a pulse of growth, a beat in its long life. Streams of stars arc across its halo, evidence of these past meals. Each stream is a scar, a rhythm carved into the giant's body. If you mapped its halo across time, you would see wave after wave, collision after collision, a heartbeat of consumption echoing through the ages. But perhaps the strangest rhythm is the one we share with it, the cycle of approach. Andromeda and the Milky Way are not static neighbors. They orbit a common center, slowly, over billions of years. Right now, we are moving inward, closing the gap. In 4 billion years, we will collide. In 5, we will merge. That collision is the next great beat in the symphony of our local group. The galaxies are already part of each other's rhythm. We are already listening to the same pulse. What if we could speed up time? What if we could watch Andromeda's history unfold in seconds? We would see it flicker, flare, dim, flare again. We would see its arms twist, reform, fade, reignite. We would see its halo ripple with the streams of cannibalized companions. We would see its core flare and settle, like a sleeping giant rolling in its slumber. And all of it together would look like a heartbeat, slow, immense, patient, but steady. This is not only poetry. Astronomers detect these rhythms scientifically. They measure the star formation history of Andromeda by studying populations of stars at different ages. They simulate mergers on supercomputers, watching galaxies collide and settle into new shape. They trace the density waves of spiral arms, calculating their speeds and lifetimes. And everywhere, the same truth emerges. Galaxies are not static. They live in cycles. They breathe. They beat. And here is the haunting thought. The rhythm is slowing. In its youth, Andromeda's heartbeat was fast, violent, filled with bursts of starbirth and fiery collisions. Today, it is calmer. Its gas is thinner. Its star formation rate is lower. The giant still breathes, but more slowly, more quietly. It is moving toward the twilight of its life, when its rhythm will fade altogether. One day, billions of years from now, Andromeda's star formation will cease. Its gas will be gone, consumed or ejected. Its spiral arms will fade. Its heartbeat will stop. The galaxy will grow old, filled only with long-lived red dwarfs, glowing faintly, no new stars to replace them. That will be the last chapter, silence after a lifetime of rhythm. But silence is not yet. Tonight, Andromeda still beats. Its arms still flare with newborn stars. Its halo still ripples with the scars of cannibalism. Its core still holds the potential for awakening. The heartbeat continues, faint but steady. And we, the Milky Way, are already part of it. Our future collision will be another beat, another pulse, another chapter in the rhythm of giants. What if galaxies are not merely structures, but symphonies? What if each one plays a song across time, its rhythm written in stars, its melody carried in light, its harmony shaped by mergers and collisions? If so, Andromeda's song is deep and ancient, slow and powerful, a bass note resonating across the local group. We may be only a small harmony, a faint counterpoint, but together we form the music of the cosmos. And here lies the most profound truth. When you listen to your own heartbeat, you are hearing the same rhythm, not in scale, but in essence. Your heart beats with cycles. You breathe in and out. You live in pulses of time. Andromeda does the same, on a grander stage. The giant galaxy and the fragile human share the same pattern. Both are temporary, both are rhythmic, both are part of the same cosmic music. Tonight, as you close your eyes, imagine Andromeda not as still, but as alive. Imagine it breathing, pulsing, beating with rhythms too vast to see. Imagine that every flicker of starlight is a note in its song, every merger a drumbeat, every spiral arm a wave of melody. Imagine that you are listening to its heartbeat across the silence of space. And imagine that, in some way, your own heart is keeping time. But our journey does not end here, for if Andromeda has a heartbeat, then so too does the universe itself. The expansion, the acceleration, the cycles of creation and destruction, all are rhythms of something greater. To understand Andromeda fully, we must step beyond galaxies and listen to the heartbeat of the cosmos. That is where our journey turns next. Part 20. The Final Symphony. There is a silence that only comes at the end of a journey. A silence filled not with absence, but with resonance, like the last note of a symphony still trembling in the air. We have walked through the story of Andromeda, its size, its weight, its chemistry, its fire, its history, its heartbeat. We have followed it from birth to destiny, from collisions to creation, and now we stand at the edge of its song, listening for the meaning beyond the science. Andromeda is a galaxy, yes, 1 trillion stars, a halo of dark matter, a history of mergers, but it is also something more. It is a mirror, reflecting back to us the deepest truths of the universe. It shows us that nothing is still, that every system breathes, that every life, whether a human or a galaxy, has a rhythm, a timeline, an end. And yet, within that ending, there is beauty. Within that inevitability, there is wonder. Think of the cycles we have traced. Andromeda was born in the fire of the early cosmos, grew through collisions, lit the sky with quasars, quieted, and still shines with new stars today. One day, it will merge with the Milky Way, creating a galaxy even larger. One day, its fires will fade, and it will glow with only faint embers. But even then, its atoms will remain, scattered across eternity. Its story will not vanish, it will transform. Is this not our story too? We, too, are born from fire, forged in stars. We, too, grow through collisions, through challenges, through transformations. We, too, shine for a while, and then fade. But our atoms remain. Our essence continues. The galaxy's destiny is our destiny, written in the same physics, the same rhythms, the same silence. What if galaxies are not only objects, but teachers? What if Andromeda's presence in our sky is not only coincidence, but invitation? An invitation to look up, to wonder, to see ourselves as part of something larger. When you gaze at that faint blur, you are not just looking at another galaxy. You are looking at your own future. You are looking at the place where the Milky Way will dissolve, where Earth's atoms will scatter, where our story will merge into something greater. And yet, this destiny is not frightening. It is calming. The collision is billions of years away. The stars will rarely strike one another. The cosmos is vast enough to absorb the chaos. And by then, we may no longer be here, or perhaps we will have grown, moved, spread. Perhaps our descendants will watch the sky from worlds orbiting alien suns, witnessing the union of giants with awe, writing myths as humans always have. Perhaps the collision will be their story to tell, their Andromeda to remember. The more we look, the more we see that Andromeda is not only a scientific fact, but a cosmic poem. Its arms are stanzas of light. Its core is a chorus of age. Its halo is a whisper of ghosts. Its destiny is a crescendo. And we are part of that song, listeners and participants both. What if the entire universe is a symphony? Every galaxy a note, every collision a chord, every heartbeat a rhythm. If so, then Andromeda is one of the deepest notes in our cosmic neighborhood, resonating across time, shaping the harmony of the local group. We are small, yes, but even the smallest instruments contribute to the music. Our lives, our thoughts, our hopes, they too are part of the song. Tonight, as you rest beneath the quiet sky, imagine this final vision. The Milky Way and Andromeda, no longer separate, but one. Their arms tangled, their cores united, their stars blended. Imagine standing on a distant world and seeing a sky filled with streams of light, brighter than any night Earth has ever known. Imagine knowing that you are not watching destruction, but transformation. The end of two galaxies, and the beginning of one. That is the final symphony. Not silence, but continuation. Not ending, but becoming. And so we return to ourselves, to this moment, to this small planet circling a quiet star, caught in the gravity of a galaxy that is already entwined with another. We are fragile, we are temporary, and yet we are aware. That awareness is rare, that awareness is precious, that awareness is what makes the journey matter. Andromeda's story is vast, but in the end, it tells us something simple. You are part of this. You belong to the cosmos. You are not separate from the stars. You are their continuation, their voice, their memory. To look at Andromeda is to look at yourself, spread across space and time, written in light. This is the end of our journey, but not the end of the wonder. The sky will still hold its mysteries. The stars will still sing their songs. The galaxies will still dance their dance. And every time you look up, you will remember. The story continues. The symphony goes on. Before we part tonight, I want to say something gentle, something from the heart. If this long voyage through Andromeda has brought you even a small moment of calm or wonder, I am deeply grateful that you chose to spend it here with me. A quiet like, or a soft tap on subscribe, is more than just a gesture. It is encouragement that helps me continue creating these night journeys. And if you'd like, I would love to know where you are listening from and what you felt during this story. Your words, whether a single line or a long reflection, are like stars guiding me forward. I treasure them. And so we close, not with silence, but with belonging. May your night be peaceful. May your heart be steady. May you feel, in some small way, the connection between yourself and the galaxies above. And may you carry that wonder with you, into dreams, into tomorrow, into every breath. For the universe is vast, but tonight it sings for you.